Alright, hello and welcome back to Real Seekers. I'm your host, Dale, and today I've finally finished my winter semester of the master's program, so I wanted to come back to my cosmological argument. So this is part 3b, continuing on from part 3a, where I was outlining my abductive argument that the universe probably began to exist at some point in the finite past on the basis of the scientific evidence from the field of cosmology. And in part 3a, we kind of went over, okay, well, what is the scientific data? We had the certain empirical evidences like the redshift data, the cosmic microwave background radiation, the light element abundances in the early universe. And then we had the two singularity mathematical proofs or theorems from the Hawking-Penrose singularity theorem back in 1970, and then the 2003 BVG, Bohr, Guth, and Vilenkin singularity theorem that proved the universe began to exist on certain conditions. And we were kind of using the Hawking-Penrose singularity theorem, and it postulated 5 conditions that would, if those conditions were violated, then you could escape the singularity, and the atheists and skeptics could pretend that the universe is eternal in the past and, escape a cosmological argument that way. Or at the very least, deny that we can prove the universe is contingent based on the scientific evidence. And on that front, we showed that there are only 3, what Stephen Hawking calls reasonable exceptions. 2 of the conditions are unreasonable and scientifically proven facts to be wrong. Less than 5% probability that those models are true or even possible. So really, we looked at a couple of models outside of that, and then we looked at the first reasonable exception to the Hawking-Penrose singularity theorem, which is the CTC, or closed time-like curve models. And in this part 3b, I want to pick up from that, and I want to go, okay, that one failed. But there are more those 2 other conditions to the Hawking-Penrose singularity theorem that if we postulated a violation to those, maybe that would allow atheists and skeptics to have an eternal cosmological model. So let's start getting into those models. These are the models that are most atheists and that believe the universe is eternal kind of cling to the models that we're going to be discussing here. So let's get straight into it. So the first model to cover here is what became known as the eternal, quote-unquote, quantum vacuum fluctuation cosmological models. So these are the second reasonable exception to the Hawking-Penrose singularity theorems. And they basically suppose that, well, maybe there's a violation to the strong energy condition. That the strong energy condition is typically obeyed by normal types of matter, what scientists call, quote-unquote, normal types of matter. And these, when you posit a violation of these, the strong energy condition, this is what gets you what are called eternal inflation or eternal inflationary models of the universe. And one of the earliest types of cosmological model under this category is actually one that predates the discovery of inflationary theory proper in the 1980s. And these were called quantum vacuum fluctuation models. So essentially what happened during the 1970s, it was known that at some point in the past history of the universe, specifically prior to what's called the Planck time, so that's at the 10 to the minus power of minus 43 seconds after the Big Bang singularity, within a split fraction of a second after the alleged Big Bang singularity would have taken place. The universe's size would have been so small that it would have been of subatomic proportions, and therefore general relativity no longer applies. Now it's in the quantum realm, and we need a quantum theory of gravity to apply to the universe and that sort of thing at this scale. So yeah, therefore, if we're going to explain the universe and say that it had a beginning in the finite past, well, we need to incorporate quantum physics, quantum mechanics, and see how things work in that way, and argue that the universe must have begun to exist. Or is it possible, when we introduce quantum physics and quantum gravity, that maybe the universe is eternal after all? Essentially in quantum mechanics, the creation of what are called virtual particles are things that are postulated to take place. Things just you'll hear popular level atheists and skeptics say that, well, things just pop into and out of existence all the time in the quantum realm. These virtual particles pop pop up and then pop out of existence all the time. We're kind of going back to through random fluctuations in the energy of the quantum vacuum. So this is kind of going back. Remember in part 3A when we were discussing thermodynamics, we kind of looked at Boltzmann, his hypothesis back in the 19th century. So this is kind of an updated modification of that failed theory or hypothesis or that kind of model. And it was really in 1973 that a guy named Edward Tryon first kind of speculated that, well, the universe itself, maybe it is just one of these virtual particles. It just popped into existence. However, unlike other virtual particles, it didn't pop out of existence. It's a long-lived virtual particle where the total energy of this particle is zero. So that, yeah, therefore our universe was born. It came into existence due to random chance energy fluctuations in this quantum vacuum state. So, the vacuum energy was converted into matter through quantum mechanical phase transition, process known as that, within this primordial quantum vacuum. And then, this vacuum state, at least prior to the onset of inflation at the Planck time, was thought to have existed eternally and in a steady state, just like what the scientists used to think prior to the 1920s. It's not the universe in this vacuum state. It wasn't expanding. It was just stationary and static for all of eternity. And then obviously at the Planck time, inflation would take place and the universe started expanding and that sort of thing. But under this quantum vacuum fluctuation theory, consequently, our universe as a whole is not really thought to represent the universe as in totality. It's just a mini universe within this larger virtual particle that's static, and it's not alone. There are other mini universes out there. There's a multiverse of miniature universes, all expanding, coming into and out of existence within this overall virtual particle universe that's eternal and static in this state of a primordial quantum vacuum state. This kind of gave birth to the notion of quantum vacuum fluctuation models to try and explain the universe. And you can see it here, the model in the YouTube video as to what it kind of looks like in these original 1973 and beyond notions. So what do we say by way of assessment then? So in the first place, in terms of the plausibility of quantum vacuum fluctuation models of the 1970s, essentially in terms of plausibility, these models are utter failures, total failures, as a matter of fact. It was none other than Britain's leading quantum cosmologist, Dr. Christopher Isham, who basically said, quote unquote, with respect to these types of models, they have been long since, quote unquote, jettisoned out of the field of respectable cosmogony, being seen as nothing much, and ultimately they have been totally abandoned before the close of the 1980s, end quote. These are obviously rubbish if you appeal to the atheists and skeptical scientists and world's experts themselves. Principle of enemy attestation right there. And the reason for this universal rejection of these models as false and implausible is because, look, there's this deep-seated inherent logical incoherence. They are logically impossible to be true. Because these models basically depend, again, on the Heisenberg uncertainty principle, and that makes it impossible to specify precisely when and where a quantum vacuum fluctuation will occur and start expanding out into a mini universe. Like our observable universe is this one of these mini universes within this overall static primordial vacuum, quantum vacuum state, or the universe ensemble, or whatever you want to call it. And obviously, this leads to this incoherence because it means that any finite interval of time, there's going to be a positive probability of such a fluctuation occurring at any point in space. And if we give it infinite past time, remember we're pretending it's eternal in the past, well, that means that many universes will eventually be spawned at every single point within the primordial vacuum. And as these mini universes expand and that sort of thing, well, then they're going to begin to collide and coalesce into each other. And obviously, we should by now be observing an infinitely old universe and not a relatively young one. So, yeah, the only way to avert this problem would be to postulate that there's an expansion of the primordial quantum vacuum itself. But that doesn't work either because, well, once you do that, well, that proves that the quantum vacuum is expanding, and if you extrapolate back in time, it must have, had a beginning point in the finite past itself. So yeah, according to quantum cosmologist Christopher Isham, this problem proved to be quote unquote fairly lethal to any and all quantum vacuum fluctuation models. Yeah, this is just utterly implausible. We would observe mini universes crashing into each other, but yet no mini universes collide with other mini universes, with our mini universe, sorry, or coalesce with other mini universes, and this would be expected if the universe were in fact eternal, and due to the Heisenberg uncertainty principle, random fluctuations would be happening all the time. A mini universe should be popping up in your backyard, but yet it's not. So, yeah, this is just utterly implausible, and all scientists reject it as foolishness today. Okay, in terms of explanatory scope, then, such models utterly fail to explain various detailed bits of evidences that we've gotten. And in fact, this has been shown in 2012. A very famous scientist of the BVG singularity theorem, Dr. Alexander Vilenkin, showed that even cosmological models that do not meet the condition of having on average, being in an average state of cosmic expansion, such as this quantum vacuum state is posited to be static and stationary, right? Eternal and static. It's not expanding. Even that fails to explain our observed evidences, and that was proved in 2012 by Dr. Alexander Vilenkin. So it utterly lacks explanatory scope. In terms of explanatory power, then, quantum vacuum fluctuation models, again, are woefully inadequate. So in the first place, they have a huge issue in terms of their explanatory power with respect to the various production mechanisms of matter production that are employed in the theory. These are very improbable mechanisms, or matter production mechanisms in the first place. Secondly, they contradict observable evidence, as we saw in the plausibility criterion, right? Namely, we see a relatively young age of the universe, 13.82 billion compared to eternity or infinity. Why so young? We shouldn't see that. In all probability, it's very, very improbable, almost impossible to be seeing such a young universe. And what's more, there's a total lack of observable evidence for multiple quote-unquote collision markers of mini universes colliding into our mini universe. And that should be evident in the cosmic microwave background radiation data, but yet it's not. Now, it's important to note that obviously scientists today, not advancing such a foolish model, eternal cosmological model, do have a ready answer in terms of proponents of inflationary theories or inflationary models. They try to explain away this lack of observational evidences for collisions and coalitions in the CMB data. They say, well, it was erased during the inflation process itself. But note that these types of explanations, they only work if one posits an eternal future inflationary expansion of the universe as a whole. So the virtual particle universe, not just the mini universe, has to be expanding, or the quote-unquote universe as a whole, that virtual particle can't be stationary and eternal like quantum vacuum fluctuation models posit. You can only erase this evidence if the universe as a whole, that virtual particle itself, is expanding. And that's the only way you can get this erasing defense to explain why we don't observe evidence for collisions and coalescing of the various mini universes with banging into our universe and crashing into our universe and that sort of thing. So that explanation doesn't work for quantum vacuum fluctuation models, and thus these types of models still lack explanatory power. They don't explain the lack of multiple expected collision markers within the CMB radiation data. A final issue in terms of explanatory power is, look, even if this model posits an eternal extension over infinite past time, then each of the infinite regions of the primordial vacuum, the universe as a whole, that static eternal thing overlooking all, giving birth to all the mini universes, including our own, they should have spawned an open, expanding universe, which, quite frankly, over the course of eternity, by now, it would have entirely filled that region, resulting again in all of the individual mini universes colliding and coalescing into each other. And like I said, that's contrary to the observational evidence that we have just by looking out into outer space with our telescopes, as well as what we find with the CMB, or cosmic microwave background radiation data. So this is 0%. It's logically impossible. It's actually impossible. The quantum vacuum fluctuation models of the 1970s can explain or have the power to explain the scientific data that we have. It's absolutely false based on these factors alone. Okay, finally, we have the less ad hoc criterion, or the simplicity criterion. And in terms of simplicity, the quantum vacuum fluctuation models, in order to be consistent with observational evidence, would have to be extremely ad hoc. This is to evade the issues of, the various mini universes expanding and then colliding and coalescing into each other over the course of the eternity. Basically, they just posit very ad hocly that, well, maybe the universe as a whole is not only static and eternal, but is also actually infinite as well, and that the random fluctuations that give rise to all the expanding mini universes only ever occur at distances that are infinitely far apart. And this avoids the notion that, well, they should have collided into each other and coalesced through their expansion and that sort of thing. But this is entirely ad hoc in order to solve it. And as we saw in part one, actual infinite, it's logically impossible for actual infinites to exist. So you can't avoid the problem by positing an actual infinite when, philosophically speaking, that's impossible. It can't be actually infinite in the first place. And even if there were, this virtual particle overall universe were actually infinite in its size, extremely ad hoc deposit, and all the mini universes or random fluctuations just happen to occur infinitely far apart from each other. Complete rubbish. No, there should be a mini universe. Very, very, very. It's astronomically more probable that there should be a mini universe in my backyard. It's not there. That proves this model's false. So yeah, that's I give a 1 to 5%. I'll be generous. I'll give it a 5% fulfilled on the less ad hoc criterion, given the extremely ad hoc nature of having to, number one, assume that actual infinites are true, which we've proved are false, and further, that even if it is true that the random fluctuations giving rise to many universes within this vacuum state all just happen to take place at infinitely far distances from each other. That's ridiculous. So, yeah, as we can see, this theory fails overall. It's doesn't work. It's 1% in terms of plausibility, 0%, 5% in terms of explanatory scope, 0% in terms of explanatory power, and 5% for the less ad hoc criterion. Overall, there is a 0% probability that quantum vacuum fluctuation models fulfill the best explanation inference criteria, and therefore it's, once again, it's worse. The best model we have was the last one, the CTC, or closed time-like curve models. But this isn't the only game in town in terms of eternal inflation or eternal inflationary cosmological models. Let's see what else we have on offer and see how those fare. And just before I get into that, I just want to clarify something. So obviously parts of this cosmological series were recorded 2 years ago and that sort of thing. So I just want to clarify something that I was saying wrong here. So the quantum vacuum fluctuation models posit, look, the quantum vacuum state is eternal and static, right? So I said that, but it itself isn't a virtual particle that pops into existence. I don't want you to get confused. It's the quantum vacuum, it's eternal and static, that's, over everything, and fluctuations occur within that, giving rise to virtual particles. When they're long-lasting, we call those mini-universes. So the mini-universes, like our observable universe, for example, those are the virtual particles that pop into existence from within the quantum vacuum state itself. So just wanted to clarify that, because I think in re-listening to this, it sounded a little confused at some bits, so I wanted to make sure I clarified that for people. So another thing that I would like to clarify, so obviously the main objection to these quantum vacuum fluctuation models is in the CMB, there's no evidence for collision or the coalescing of various mini-universes. And I just want to clarify that. So there is some possible candidates. So Skydive Phil, for example, has done interviews on the Proscenium, or the Ask an Atheist Anything podcast. And he's come out and said, from scientists, in the CMB data, there are about 4 possible candidates, cold spots that atheists and skeptics will say, well, maybe it's possible those are evidences of collisions and that sort of thing. But this is just total assumption. Many scientists disagree and say, no, this is not confirmation of a collision or coalescing of mini-universes at all. And even ones that do, even Skydive Phil himself fully admits this. He's like, look, you can't make a claim based on this evidence. It can be interpreted in other ways other than positing a collision. And even if it was a collision, even pretending that was a collision, just 1 to 4, we would expect over the course of all eternity there would be much more than just those 1 to 4 possible candidates that we see in the CMB. So once again, it still lacks explanatory power, even under the best of circumstances. But just so you're not caught off guard, I did want to make you aware that there are some aspects about the CMB data that some atheists and skeptics might say, oh, well, there are some evidence in favor of collisions and that sort of thing. No, there's not. These cold spots or whatever in the CMB can't be proven to be a collision or the coalescing of many universes. That's just pure non-evidenced assumption on the atheist's part in interpreting the data, and most scientists do not agree with that interpretation. So just wanted you to be aware of that. Let's move on to the next part. Okay, so essentially what happened in the early 1980s is when we started realizing that immense problems were starting to arise, and they were besetting these quantum vacuum fluctuation models that postulated an eternal static world ensemble, or this universe as a whole, this vacuum state that gave rise to these fluctuating mini universes. And what happened is scientists like Dr. Alan Guth realized that, look, the larger universe ensemble, or this universe as a whole, it itself must also be expanding. Scientifically impossible for it to be static and eternal while many universes are popping into and out of existence, as we saw with the quantum vacuum fluctuation models of the 1970s. And therefore, he said, no, that universe as a whole, that wider vacuum state itself, must be expanding in order to evade the issues that come up here. And in 1981, Guth presented what he called inflationary theory, or inflation theory, which basically posited at the earliest phase of the universe's past history, a bizarre type of energy would act like a repulsive gravity or negative gravity. So, as a kind of like how Albert Einstein posited the cosmological constant factor and just made that up. Now in 1981, Guth is saying, well, Einstein was totally out to lunch and just making things up. But it looks like maybe there's something like that could have been true. Repulsive gravity served as this repulsive force rather than an attractive force like normal gravity serves as. And this caused this super rapid inflation period in the early thing where it, doubled in size extremely, extremely quickly, within a trillionth of a trillionth of a trillionth of a second, and that sort of thing. And it went through this inflation period until it got to the size of a grapefruit, and then it returned to normal and that sort of thing. But yeah, this temporary inflation period was posited for the expansion of our own mini universe, and then finally finally our own mini universe returned to the more mundane, accelerating expansion rate that we see today. And this essentially helps. This inflation notion helps solve many of the problems with the standard Big Bang theory that came up, that many young universe creationists like to pose. So things like the horizon problem. Light can only travel so far, yet it could not have traveled as far as we see the universe, 13.82 billion light years, and that sort of thing. Or the flatness problem, the shape of the universe, or the cosmic relic, or lack of magnetic monopoles problems. These are all things that young universe creationists would bring up as problems against the standard Big Bang model. And what Alan Guth discovered is, well, by positing this inflation theory, or this inflationary period, this actually solved all of these problems. And if it happened, it resolved these issues totally. However, there was the original version of inflationary theory back in 81 had problems with it. So those would actually come to be solved a little bit later during conferences. In 1982 and 1983, out popped what was called the new inflationary theory. And this is the new inflationary theory is otherwise known today as just simple inflation theory. So we forget about the original version, and new inflationary theory is what scientists call inflationary theory today. Now, this notion of repulsive gravity, that's the notion that was particularly relevant about inflation theory and new inflationary theory, that's relevant to our argument here. And for many of the cosmologists during the 1980s and 1990s, basically they used this to speculate that, well, perhaps maybe there was this gravitationally repulsive material, and this repulsive gravity is actually the norm. This is the way the universe as a whole actually is, and it's really attractive gravity, or attractive gravitational entities that we know of and observe in our universe, like planets, stars, and humans, and stuff like that. And those are the exception to the norm, the exception to the rule of repulsive gravity in this inflationary universe as a whole. And it was based on this that physicists like Dr. Andre Lind and others argued for eternal inflationary cosmological models. So the inevitable question at that time was, well, could these inflationary models be eternal in the past? And in the 1980s, 1990s, there was a whole proliferation of inflationary type models, eternal inflationary type models, with hundreds of variations of these types of models being developed and that sort of thing. And they fell, during this time period, they fell under one of two categories. Either they were considered a new inflationary model or just a regular inflationary model, or they were what was called a chaotic inflation model, which is what Lind developed back in 1986. Yeah, there's a bunch of models. There's the chaotic types. There was the 1986 chaotic inflationary theory. There's also the string landscape, otherwise known as the swampland inflationary models that you guys can see on your YouTube screen here. But yeah, ultimately, this flurry kind of ultimately broke down in 2003 with the BVG, Board, Guth, and Vilenkin theorem. This falsified all of these various models, or most of them. And you'll remember when we covered that in part 3A, there are now four conditions or four exceptions for that BVG theorem. And eternal inflation models of the 21st century only qualify under these conditions. So all the other ones have been scientifically falsified. They're impossible to be true, given the BVG singularity theorem. Also, these models had issues with the second law of thermodynamics and the entropy properties of the early universe. In 2004, it was none other than Stephen Hawking who famously kind of admitted, look, information is preserved in both black hole formation and evaporation. Yeah, there's no... at the time, black holes were thought to be the mechanism where the mother universe would give birth to a baby mini universe and that sort of thing. But given what Hawking found, this is scientifically falsified, because if this were the cause of the universe, well, then we wouldn't have the observed low entropy condition of our mini universe and that sort of thing. Also, these types of models suffered from the old Boltzmann brains problem, which reemerges. Dr. Roger Penrose, for example, says that the odds of our universe, quote unquote, quantum fluctuating into existence with the early universe's low entropy condition is 10 to the power of 10 to the power of 123. Just compare that to the probability of the solar system forming by sole random chance, particle collisions and that sort of thing. That's 10 to the power of 10 to the power of 60. So this is astronomically improbable, and it's in fact statistically impossible to happen. Somebody must have designed that. It must have been the Lord our God that designed the universe, because Bill Dembski kind of proved that the law of universal probability bound is 10, anything that's less than 1 divided by 10 to the power of 150 is impossible, mathematically impossible to occur by random chance and that sort of thing. So this is astronomically more improbable than just 10 to the power of negative 150. I think that kind of says it all. Finally, I want to give a quick quote to Dr. Alexander Vilenkin. He's the V in the BVG singularity theorem from 2003. Look, he kind of, with respect to these early inflationary models from the 20th century, from the 80s and 90s, he just says, quote unquote, look, it is said that an argument is what convinces reasonable men, and a proof is what it takes to convince even an unreasonable man. With the proof, absolute proof, now in place, cosmologists can no longer hide behind the possibility of a past eternal universe. There is no escape. They have to face the problem of a cosmic beginning. We have no viable models of an eternal universe. The BVG theorem gives us reason to believe that such models simply cannot be constructed. Those are some powerful words from the world's expert here, Dr. Alexander Vilenkin. But yeah, as we said, all eternal inflation models of the 21st century really just develop new models. They've completely abandoned the 80s and 90s garbage as being falsified thanks to the BVG singularity theorem. And instead they go for, okay, well, we have those four exceptions, those conditions, in order for the BVG singularity theorem to be successful, kind of like what we're doing with the Hawking-Penrose and the 5 conditions there. And they'll deny, or they'll try to violate those 4 conditions in order to make an eternal inflationary model work. So what are those four conditions again? So again, it's number one, there's infinite contraction, or de Sitter cosmology, it's called. The second is, okay, well, you can say, well, there's an asymptotically static space. And these give rise to emergent model classes. The third way you can go about it is, okay, well, there's infinite cyclicity. The universe is cyclical in nature, kind of like the oscillation model, but it's more of an update this time. And you have things like the Baum Frampton, or the quote unquote phantom bounce model, so to speak. And then the fourth and final way is, okay, well, you can go into time reversal or time deconstruction models at the singularity. And these are advocated for by, the most famous and most developed model of this type are like the Aguirre-Grattan model. But also, the atheist Dr. Sean Carroll, he goes for this type of model too. But he doesn't have like a fully developed model on offer. If you want to go with this fourth condition, the Aguirre-Grattan model is the best you've got. But yeah, those are the four ways that you can escape the BVG singularity theorem and posit an eternal inflationary model of the universe. Obviously, in addition to that, there is the fifth condition or exception, which we'll get into, which is its own category, which is that those quantum gravity models. Okay, so getting into eternal inflationary models of the 21st century based on the four exceptions to the BVG singularity theorem. The first are based on infinite contraction models. So these are types of eternal cosmological models that are kind of like an hourglass. They posit that there is an infinitely spatially contracting phase of the universe immediately up to the point of singularity, and then all of a sudden the universe bounced and started expanding, which is the phase of the universe that we're seeing right now. So this is kind of a single infinite bounce, quote unquote single infinite bounce type model. And by that token, it avoids all the problems that the traditional oscillation models came up with, because they posited multiple contraction and expansion. This says, nope, it contracted from eternity past, and infinite eternity past, arrived at a singularity, and then boing, and then bounced out into the expanding phase. So there's only this one bounce that's posited under these. So, examples of these types of infinite contraction models are things like the Mixmaster universe model. Or a better one, I think, is the de Sitter universe model. And basically, they'll avoid the inevitable finite past boundary, which is implied by the BVG theorem, by saying that, well, hang on, look, on the BVG singularity theorem set only works that by assuming, on average, the universe is in a state of cosmic expansion. And this model says, well, look, it's not true that on average the universe was in a state of cosmic expansion, because there was a prior phase that was in an infinite state of cosmic contraction. So the contraction and the infinite expansion phase not only cancel each other out, but these models postulate, look, on average, the universe is in a cosmic state of negative expansion. It's actually contracting on average. It's shrinking on average. It's not positively expanding and that sort of thing. Whereas other models will say, no, there's a net balance, so it's exactly zero. It's not expanding or contracting on average and that sort of thing. But that's the next model. We'll get to that. But yeah, these models say that instead of having an on average positive expansion rate, it has an on average negative expansion rate. That's how the infinite contraction models escape the BVG singularity theorem, in denying that assumption that on average the universe is in a cosmic state of positive expansion. You can see the pictures of the model in the YouTube video. That'll help you guys make sense of, it's kind of like an hourglass model standing up. And obviously notice it doesn't necessarily have to go to that singularity point before the bounce, right? It doesn't go all the way to a cone and then bounce out. It can only go so far, and then it bounces out. So it doesn't necessarily have to go to a point of singularity there. Okay, the next eternal inflation model that's of the 21st century that we're going to be looking at is the asymptotically static space-time model. And these models posit, once again, on average, over infinite time, that the expansion rate of the universe is zero. And therefore, it's not the universe is not on average in a state of positive cosmic expansion, and the BVG singularity theorem does not apply to it. So it's kind of reminiscent of, remember that old Albert Einstein, who was so biased in believing in this old steady state model. Well, this type of cosmological model goes back to that, and it kind of posits that, well, perhaps the universe existed in an eternal steady state, and then suddenly it just began to expand, just as we see it today. But on average, the expansion rate is zero for the entire history of the universe. Once infinity is, put into the averaging calculation there. So despite all of our observational evidence indicating that on average the universe is in a positive state of expansion, really due to this eternal steady state phase, over the course of infinity or eternity past, it's really zero. So yeah, a way to explain this model is, and how this works, is just imagine the city of Toronto. It all of a sudden changed its property tax rules to say that, okay, instead of taxing people based on their individual property assessments, people are going to pay taxes now on the average value of property per meter in the city. And then through this averaging process, obviously those living in higher end properties, they're going to end up paying less because their property tax rates are based on the total property per meter, and that's going to include poor people properties and their things, so they're living in a mansion and they're paying less. Likewise, those in lower end properties, they're going to see their property taxes go up because now they're being tax rates are factored in with the rich mansion properties and stuff like that. So that's how the averaging process would work. And now pretend all of a sudden you include the Sahara Desert, and pretend this is the infinite Sahara Desert. A large portion of square meters of basically worthless property are just suddenly thrown into the averaging calculation. What's that going to do? It's going to drive it down. So the average value per square mile would drop considerably. And if the Sahara Desert were composed of an infinite number of square miles, which is what this model posits, an eternity, past eternity of no expansion rate, zero expansion rate, well, then that means the average property value is going to shrink to zero. So yeah, they say, well, that it's the same with the expansion rate. Yeah, it's from what we see, it's now in a positive state of expansion, but averaging everything together, it's really zero, because we have an infinity of it not doing anything, not expanding nor contracting. So yeah, but basically these types of models use this escape route, and they're typically classed as quote unquote emergent models by physicist Dr. George Ellis, for example. And they postulate that over eternity past, the universe existed in this infinite steady state of zero average expansion, which is sometimes called the Einstein static state, or ESS. And then suddenly, through inflation, it transitioned into this positive expansion phase that we observe today. And it's important to note here, so here's an interesting note, that the most recent and the best of these types of models actually straddle two categories. It's known as the emergent model. And this uses kind of a low energy solution of loop quantum gravity. So it's associated with a quantum gravity model as well. It fits under eternal inflation and quantum gravity. It uses loop quantum gravity, which we'll find out a little bit more about in subsequent sections as we go along. But yeah, it has to do this to make the perturbations within the Einstein steady state portion of a limited size. Yeah, so yeah, that's it. In terms of this model, take a look at the YouTube video if you want to see visual images of what it's like. One thing to note, many versions of these types of models aren't actually eternal in the past at all. They actually entail a finite beginning to the universe. And George Ellis, his most recent work, pertains to these types of finite versions of the models. Okay, so next up we have the third exception to the BVG singularity theorem, for eternal inflationary models, and these basically represent infinite cyclicity or cyclical models to the universe, kind of like the old outdated oscillation models, but with an update. So let's find out about those. Okay, so infinite cyclicity models are kind of like the oscillation models, and obviously there's that thermodynamics issue, that buildup of thermodynamics from cycle to cycle that says that this is impossible to be true. And basically, cosmologists Paul Frampton and Loris Baum have recently proposed kind of an ingenious solution to avoid this thermodynamics or entropy buildup problem that where the entropy is conserved from cycle to cycle through what they call the Baum-Frampton phantom bounce model. And what the phantom bounce model posits is some kind of special type of dark energy that has a super negative equation of state, something less than -1. And that leads the future expansion rate to accelerate to such a great level, even up to infinity itself. So, again, assuming actual infinities, that our visible horizon actually starts to shrink over time. And then the universe splits into a non-interacting or causally disconnected patches of sorts. This is why the process is called the Big Rip. The patches are being ripped away from the universe as a whole. And then these patches contain no ordinary matter, no energy, radiation, zip, absolutely bubkiss. They only contain this phantom dark energy. And as such, all of the problematic entropy buildup issues that related to the old outdated oscillation models are consequently solved because hypothetically all of the entropy buildup is contained within the thinly spread ordinary matter and energy in the rest of the overall expanding universe as a whole. The mini universes or the patches, they undergo deflation. They start contracting in amounts exactly equal to the total overall expansion rate of the overall universe or universe as a whole. So the patches are contracting in exactly the same proportion that the universe as a whole is expanding. They cancel each other out, therefore it avoids the BVG singularity theorem because again, you can't say that the universe as a whole is positively expanding on average. It's canceled out by these contracting patches. And then obviously from that, all of these patch universes deflate down to a singularity, or at the very least a near singularity scale. And then they fractionate. They produce new Big Bang mini universes, each of which then propagate in this exact same manner. So it's a perpetual cycle. They start expanding just like the original universe, and then a big rip occurs within them, creating patch universes. They disintegrate, create new Big Bangs, and so on and so forth. So this is how this cyclic model takes place, this kind of beginningless cyclic behavior through constant big rips of patch universes from an overall universe and that sort of thing, where the patch universes can deflate or contract exactly equal to the overriding universe's expansion rate. And yeah, that's what these models are. Take a look at the screen. You'll on YouTube you'll see a visual image to help you with that. Okay, finally we have the fourth and final exception to the BVG singularity theorem, or proof that the universe began to exist in the finite past, and these are through time reversal or time deconstruction at singularity models. And these models posit basically a reversal of time's arrow, where time is understood in terms of the thermodynamic properties of the universe. So this is a naturalist, physicalist, or atheistic understanding, right? It doesn't go for the A theory of time. It must assume the B theory of time is true, and that time's arrow is purely naturalistic. It's explained solely in terms of the thermodynamic properties in the second law of thermodynamics. Going less entropy, always going to more entropy. That's what defines time's arrow. or directionality and that sort of thing. Now, models under this category of evasion strategy, they include models like Doctors Anthony Aguirre, Stephen Grattan, as well as the Chen Carroll, Dr. Sean Carroll, that famous atheist who got his rumps handed to him by Dr. William Lane Craig in a debate a few years back. So Dr. Sean Carroll and Jennifer Chen, they go for these types of models as well. Now, unfortunately, these models actually entail a low entropy, quote unquote, thermodynamic beginning of the universe at the singularity, with two independently existing expanding universes. So both have their own kind of arrows at time. So that, picture the singularity or the near singularity, because it doesn't have to go exactly to that point in the cone. It can start, remember the hourglass, from the first exception that we looked at, infinite contraction models. Picture that same model, the hourglass, but this time time's arrows right in the middle. We're in the expanding phase, but then there's this infinite contraction phase, and time's arrow actually works backwards to time's arrow in ours. So it's actually the exact reverse in terms of time's arrow or directionality compared to how we experience time in our half of the expanding as opposed to the contracting part of the universe. The arrows of time are basically reversed with respect to each other at the point of singularity or the near singularity. And you'll see it on the YouTube screen for what I'm talking about here. Just to clarify my terms, so this isn't an infinite contraction model. So this universe that has the opposite or reversed time's arrow, or time's direction is reversed compared to ours, is a totally separate universe. So it's contracting from our perspective, from our universe, our half of the universe, but technically speaking, no, it's just another separate expanding universe. It's just expanding with time's arrow in reverse. So we are its past. From its perspective, we're a contracting universe, and we're its past, just like we think it's our past. But technically speaking, this model just posits two totally independently separate expanding universes that have nothing to do with each other, apart from the fact that they share this same state of low entropy beginning point, and they have to go off in totally different second time streams and that sort of thing. So just wanted to clarify that. So this isn't the same as an infinite contraction thing. It's not like, oh, our universe has a contraction phase in its past. No, the time deconstruction models posits two separate universes, both of which are expanding, and they share this beginning low entropy state. That's it. This model basically posits two separate universes. There's not just one universe to explain, there's two separate observable universes, and they just share a common finite low entropy beginning point at time zero, what we call quote unquote time zero. Nothing in the universe expanding under negative time is causally connected to our universe. So this other universe that has an opposite direction of time, it's not causally connected. Impossible, scientifically speaking, for it to be causally connected to us. It's not a part of our past, causally speaking and that sort of thing. It's not a prior phase of our universe that caused us to come into being, in terms of our positive time universe. So really, in other words, the other side of this, what's called a de Sitter space, is not our past. There simply is no causal or temporal connection between the two universes apart from their common low entropy beginning point in the finite past. And these models, they're kind of problematic for those holding to an A theory of time, as I said before. And they have various metaphysical objections. But it's important to note that these models are actually perfectly consistent with the truth of our argument. They actually imply a absolute beginning of the universe at this low entropy point to our universe, at a finite point in the temporal past. Some people have made this argument that time deconstruction models could actually be seen as finite in nature. nature as opposed to infinite. I'm not going to assess these finite things. Remember, we've given an unspecified finite universe model. That can include Dr. Alexander Vilenkin's finite model. Maybe it's a time deconstruction model. We don't really care about the details of that for our purposes. Here, when we're looking at the specified eternal cosmological models, so we're only caring about the infinite time deconstruction models, ones that posit an eternal past, not a finite past, and that sort of thing. So that's what we're assessing here. I think that covers it in terms of explaining how these models work. So yeah, with that said, let's get into assessing these four different types of models, or these four categories of cosmological models that are eternal and allow us to avoid the implications of the BVG singularity theorems and supposedly give us an eternal universe in the past. Yeah, let's start with plausibility. So what I'll do here is I'll assess, again, all four of the models for each separate criterion. So any model that applies to plausibility, I'll deal with all four of those, all of the models that apply for that under the explanatory scope. Then I'll deal with all four models in light of that criterion and that sort of thing. So I'm not going to deal with each model separately one at a time. I'm going to look at each criterion and then tell you how each of the four models relate to that specific criterion. So it's kind of what we did in part 3A when we had, with the steady state model, we also had the updated quasi steady state cosmological model to assess as well. So we're going to do it that way. Okay, so let's get into it. So starting with plausibility. Okay, so obviously these kinds of models, like infinite contraction models, postulate actual infinites, for example. And as we saw in our philosophical arguments in part 1, actual infinites are logically impossible to exist. So these models lack plausibility in that insofar as they posit actual infinites, like with an actual infinite contraction model, for example. There's the contraction phase prior to our expansion phase is actually infinite. Even though our expanding phase is only a potentially infinite, these models claim, no, there was an actually infinite contraction phase prior to it, and that sort of thing in the past. And that's logically impossible to come about. Now, that said, I want to keep the scientific abductive argument here as independent as I can from the philosophical arguments we did before. So I'm actually, for the sake of argument, going to give it a pass here, but understand, just like we did with the A theory of time, and that these are reasons to think that these models are implausible. If they posit a B theory of time and we know that the B theory of time is false, then that's a reason to think these models fail. Likewise, if we have reason to believe that actual infinites can't exist and these models posit actual infinites, well, then we know that they're implausible, they're false, and implausible to be true on that basis. But I'm personally just separating those away from these arguments to keep it as independent as possible, to help out the atheists and skeptics as much as I can. I'm trying to be a good guy to them. So yeah, I think on plausibility, these models, for the most part, work as being plausible. There's one exception, and that comes with the phantom bounce type models. I think that they can be said to lack plausibility in various ways. So in the first place, these models require that what's called the Hubble radius of the universe, that has to diverge at the moment of turnaround, at that big rip event where the deflating patch universe rips away from the overall expanding universe. But yet, for some reason, the causal horizons, those have to be stipulated to be frozen in at the point of deflation. And then that remains intact throughout the entire process of deflation. And this just violates everything that we know about causal horizons, because causal horizons, these only represent the horizon beyond which neither light signals nor anything else with mass could have had time to reach, right? It's a hypothetical limit. But it's not like there's actually a physical barrier out there, right? So the young universe creationists used to give, before we had inflation, used to give the horizon problem as a major problem. But it's important to note that that horizon isn't a physical barrier, right? There's no reason why there would be this quote unquote freezing in at the moment of the big rip or at the moment of deflation. There's nothing physical to stop it. This is just a hypothetical barrier about how far our light could travel within that thing. So yeah, causal horizons are obviously observer relative. Event horizon of a black hole is in fact an objective physical barrier for light and stuff with mass. There's something physical there blocking it. You can't get out once you're in. There's a physical barrier at the event horizon of a black hole. But there's nothing here at this moment of the big rip that could be said to be a physical barrier and freezes in these. It freezes in and locks in at the time of the big rip or at the moment of deflation. So yeah, this model lacks plausibility. It's implausible to be true because there's no mechanism that would allow it to be frozen in the way needed for the model to be true. And thus, yeah, there's no reason why, at the moment of the big rip, why the universe splits into separate domains or patches rather than just having one single global collapse and contraction. So yeah, the Baum and Frampton phantom bounce model is wholly implausible in my opinion, given the laws of physics as we understand them. And they even have to make an ad hoc assumption, which is kind of getting ahead of ourselves here, but they modify Friedman's equation with an inverse Hubble parameter, and then they postulate that, well, maybe some unproven extra-dimensional brain dynamics are at play in stopping the expansion and then leading to the contraction or something like that. So given that freezing in issue and the lack of a physical mechanism, I assign a 5% to 20% proven fulfilled for these models on plausibility. Very generous, so I'll give them 20% just to help out the atheists and skeptics, but let's be honest, it's ridiculous at that point. Okay, next up we have explanatory scope. How do these four models deal with explanatory scope then? Okay, so in terms of explanatory scope, once again, I think that most of these models perform quite well in explaining all of the data. So a couple things. So with infinite contraction models, someone might argue, well, some of these types of models do lack explanatory scope because they only account for quote-unquote ordinary matter. They totally ignore any and all effects of dark energy in their contraction phase calculations. So these types of models would lack explanatory scope and fail and be scientifically falsified on that basis. However, if you are a proponent of the infinite contraction model, there are other models within this category, like the de Sitter universe model. These are the ones I favor of this type. And those do account for dark energy. So therefore, yeah, it does allow for more realistic infinite contraction explanation, and it does include explaining dark energy as part of its scope. Another potential thing for some of these models is that Dr. Alexander Vilenkin, in I think 2012, he updated the BVG singularity theorem so that the former requirement that it only works if we assume, on average, that the universe is in a state of positive cosmic expansion, that's no longer needed. Absolute proof that the universe began to exist in the finite past, even if we don't assume that. So all of these models are based on trying to deny the fact that the universe has been in a state of cosmic expansion, positive cosmic expansion on average throughout its entire history, and they deny that. Alexander Vilenkin, as of 2012, says, who cares? Too bad, so sad. We've destroyed you atheists and skeptics because we can prove mathematically that the universe began to exist regardless. Now, this is quite the claim. This is a little bit more controversial. It's not as universally accepted as the BVG singularity theorem from 2003. And for that reason, despite the fact that I'm personally convinced by Dr. Vilenkin's newer and more up-to-date work here, I'm not going to assume that in this show. I'm going to stick to the 2003 BVG singularity theorem that is grounded on that assumption, which means that these models are in play. But just understand, with explanatory scope, there have been updates post 2003 that no longer that give singularity theorems and don't even require that one basic assumption of having the universe on average in a state of positive cosmic expansion. So if that's the case, then all these models, see you later, you suck. You try to deny an assumption that's not needed. We can still prove the universe began to exist. And it's absolute proof, according to Dr. Alexander Vilenkin. But again, I'm just going to assume tentatively, because I don't know too much of the details about the newer work, and I know for a fact it's more controversial. I'm just going to rely on the 2003 BVG theorem, which is universally accepted as proof, and say, okay, fine, let's give these models 100% proven, all four of them, with a possible exception. There is something here about, again, with the phantom bounce models that I need to mention, and because it, at least at face value, it lacks explanatory scope in needing to change the laws of physics. They modify Friedman's equation through this inverse Hubble parameter just in order to work. And as I said above, that's something that makes it lack plausibility and that sort of thing. Yeah, again, these models do at least attempt to account for the Friedman equation, and they modify it and that sort of thing, and that's how they account for this evidence. They say, well, it needs to be updated or modified with this inverse Hubble parameter. So yeah, I'm going to assign 100% fulfilled tentatively on the explanatory scope for all four of these eternal inflationary cosmological models. So far it's 100% for all of them except for the phantom bounce on plausibility. The phantom bounce type models got 20% assigned on plausibility. Then with explanatory scope, 100% proven fulfilled this criterion tentatively, just due to I'll need more information before I'm comfortable saying I'm warranted in assigning something. So I'm just assuming a not applicable or 100% proven fulfilled as a tentative measure until I have proof otherwise on the explanatory scope criterion. Okay, wow, so far it's looking pretty good for the atheists and skeptics in terms of these models. Anyways, so explanatory power. What do we make of these models in terms of explanatory power? How well do they explain the facts or the relevant facts that we covered in part 3a? So let's start with the infinite contraction models and see how these types of models do. The first exception to the 2003 BVG singularity theorem. Okay, so in terms of the infinite contraction eternal cosmological models, these lack explanatory power in my opinion because it takes extreme effort in order to account for a central problematic fact about our universe. And this is the phenomenon of what's called quote-unquote BKL chaos problem. And so the BKL chaos is named after Doctors Berlinski, Katalinikov, and Lifshitz. And essentially, it demonstrates that any and all infinite contraction models that postulate a past eternal timeline, and which introduces a pre-Big Bang phase that kind of bounces from a prior infinite contraction phase into a present expansion phase, is very probably physically impossible to occur. And this happens because there is this collapse, which becomes chaotic as the universe is collapsing or contracting, approaching that near singularity and or near singularity point where it's about to bounce and start expanding. It becomes chaotic as it approaches this, and there's this effect of BKL turbulence, so to speak, that says that the universe will not expand at exactly the same rate in all directions. One direction might contract while the other two dimensions of space start expanding, and it'll lead to this weird expanding pancake, as the scientists call it. And that'll result in oscillations. And at that point of singularity or near singularity, there would be an infinite. At the point of singularity, if we postulate it went all the way down, there would be an infinite number. Or if it's a near singularity, there would be a near infinite number of these oscillation perturbations or turbulence issues of black hole formations, as they're called. And this is just inconsistent with our knowledge. So I give this, it's proven beyond reasonable doubt that these infinite contraction models, given the BKL chaos problem, just cannot be true. 4.99% as a generous probability that it's proven infinite contraction models fulfill explanatory power. Okay, what about the next one, the asymptotically static eternal cosmologically inflation models? Well, these are inherently unstable, and they cannot therefore be infinite in the past due to an inherent unstable equilibrium. So essentially, it relies on quantum gravity, right? Remember loop quantum gravity, and that sort of thing. And these are inherently unstable or metastable. They involve small fluctuations, given Heisenberg's uncertainty principle and that sort of thing, in the size. Any small fluctuations in the size of the universe, and thus it simply cannot remain in balance for an infinite time. Even the smallest perturbation of even a near ESS state, remember that stands for the Einstein steady state, even the smallest perturbation here would effectively disrupt the entire state, just as well as the perturbation in the genuine ESS state itself. So it cannot remain stable for all eternity. Remember, asymptotically static models say it was stable, and then all of a sudden it just started expanding out of nowhere. And on average, given the infinite zero expansion rate in this ESS or Einstein steady state, before its positive expansion state, it just averages out to zero. That was what this model said. And this objection is saying it's physically impossible and or extremely, extremely improbable that the ESS state would be stable for all of eternity past. That's just impossible. The slightest perturbation would destroy it, and given what we know of quantum thermal fluctuations, it's impossible. Yeah, this model is forced to collapse. It cannot last for all of eternity. And again, you can't say, okay, well, maybe there was no quantum or thermal fluctuations in this model, and that's how it remains steady. Well, no, this model, in order to work, this model has to assume that there are quantum or thermal fluctuations. Those are necessary to get the universe to all of a sudden start expanding, as we see and observe as a scientifically proven fact today. So you can't get off the hook that way. So, it woefully lacks explanatory power in this case, and it's very, very improbable. Even with positing loop quantum gravity, that qualification there, again, we'll address that in the next section on quantum gravity models proper, but yeah, even with that, the initial state would still be metastable. And again, any perturbation of any size, even when insufficient to initiate inflation and expansion transition on its own, would eventually cause the universe to escape the Einstein steady state, and that will mean that the system can merely last for perhaps a long, but still finite time only. It cannot last for an infinite amount of time in the past. Physically, very, very, very extremely improbable, if not impossible, for that to be the case. As the world-famous expert Dr. Alexander Vilenkin says with regards to this, he explains it thusly, quote-unquote, look, there are classical physics models for this static universe to sit there forever and then suddenly start expanding. But what we showed is that quantum mechanically, this universe is not stable. Quantum mechanics is the branch of physics that describes the behavior of subatomic particles and assigns probabilities to events. And then he goes on and says, look, for example, in classical or Newtonian physics, if you put a ball in a cup, it will not get out. It will sit there forever. But quantum mechanically speaking, objects can tunnel through. If I sit there long enough, there is some probability I will tunnel through this wall, and then I will be in the corridor. Of course, the probability is very small, but it is non-zero. And given eternity past, it's a guaranteed certainty almost that it would happen. He goes on. What we showed in our paper is that this closed static universe also has a probability of collapsing quantum mechanically. Its probability of collapse is non-zero, and therefore it could not have lasted or existed forever over eternity past. So this emergent cosmic egg scenario, if you include quantum mechanics, and we should because this model requires quantum mechanic fluctuation and thermal fluctuations in order to work, then it's simply not viable. Boom. Given the metastable and unstable ESS states, it's just utterly unexplained and lacks explanatory power as to how the universe began to exist. It must have a finite lifetime in the past, and that's what Dr. Alexander Vilenkin says. So yeah, I would assign a generous 5%, 1 to 5% proven fulfilled for these types of models on the explanatory power criterion. Okay, what about the phantom bounce or infinite cyclic models like the phantom bounce model? Well, these lack explanatory power in relation to the second law of thermodynamics, because in supposing that entropy must be zero at the big rip event, the model would be an absolute failure if any matter or any radiation were to be present, and yet this model posits an infinite amount of matter and radiation being produced over past eternity. And the only way they can avoid this increasing entropy problem is just to simply shove that entropy into another causally disconnected patch or universe, or quote-unquote exterior region, and then retain only one patch universe whose entropy thereby drops to zero, and solves this issue. Now that is incredibly forced, incredibly vague, and therefore lacks explanatory power. I mean, especially because the problem with this fanciful solution is really that it's tremendously strained on the part of the cosmologists. Even fellow cyclic model proponent Dr. Xin Zhang has conclusively proven mathematically that this model would be immensely improbable to be true, due to the problem of the various patch universes colliding with each other and thereby coming into causal contact once again over infinite time. The mechanism to create this big rip turnaround event, at least proposed under these models, it leads to a Hubble radius of infinite value. And that means that all those separate patches of the universe that have been ripped away from the main universe, they shouldn't be disconnected. In all probability, they'll be connected, and light signals should propagate and interact among these various patches. So it's inconsistent with what we would expect and very improbable to be true. It lacks explanatory power based on what we know in terms of the laws of physics and what would really happen. Even worse for the phantom bounce model, as well as all other infinite cyclic models like this, are that these are thermal models and they require quantum fluctuations. But if you allow for that, inevitably we would expect matter to be spontaneously produced through these quantum fields, and this matter that's spontaneously produced through the quantum fields, it would take on what's called a quote-unquote ergodic property as the space in these patch zones shrinks or deflates or contracts in these patch universes. This created matter would dominate the energy density and produce a dense quote-unquote fluid of black holes, and that would obviously lead to the thermodynamic or entropy buildup problems, that we were trying to avoid, and this would lead to what's called a quote-unquote black crunch event. So yeah, instead of an infinite cycling event, bottom line is, look, cyclicity is near physically impossible under these conditions, the conditions stipulated in this model, these types of models. So, yeah, they're very improbable. I assign it a 1% proven fulfilled in terms of the phantom bounce or infinite cyclical models to be able to fulfill the criterion of explanatory power. Now, finally, you may have noticed I haven't been really mentioning anything to do with the time deconstruction or time reversal models, and the reason for that is I don't want you to get confused. So remember, I mentioned that even assuming those models are true, they are not infinite or eternal cosmological models. They're actually finite because they postulate two entirely separate universes, so each of which are potentially infinitely expanding through their own time arrows in opposite directions. The only thing they share is a beginning at time zero, at a low entropy beginning state at time zero. But time zero was a finite time ago, 13.82 billion years ago. It's not eternal. Likewise, the other universe isn't our past. It's, if you want to say, well, the second universe is infinitely expanding outwards with a different direction of time, that's great, grand, and groovy, just like our thing. Number one, that's a potential infinite, not an actual infinite. Number two, if you even want to say, well, that's a actual infinite, it's nonetheless not part of our past. And therefore, even a B theory of time where there's an actual infinite and stuff like that, where both universes are actually infinite or something like that, into the future, their respective futures, given their respective time arrows, we still have a finite point in the past where the universe begins to exist. Each separate universe begins to exist at time zero, and time zero is still at a finite point in the past, 13.82 billion years, and we can presume it's 13.82 billion years on the second universe. That it's been around for 13.82 billion years as well. You can assume that. Now, just one quick objection that a lay skeptic might throw up. So obviously the world's experts, including Dr. Sean Carroll and every single scientist in the entire world that advocates for these models, says nope, the universes are definitely two separate universes with two separate time arrows and that sort of thing. And think about it, if a lay skeptic, someone like Darren Lute, he might be so foolish that he would believe something like this. He might come to you and say, well, no, there is just the one universe, and they just have two separate time arrows or something, but it's the same universe. They're not separate, so therefore it's infinite on one end in the past and infinite on the other end, and therefore we have an eternal universe because it's all one universe. Kind of like that's exactly what the infinite contraction model is, but it's just this with this positing two separate time arrows. Well, that is impossible and doesn't work, and is very, very foolish. It's why the world's experts that advocate these models would never say something so dumb. Because, well, what is times arrow? Well, it's basically the increase in entropy equals time. So entropy, we have this beginning, time zero, this low entropy beginning state. The universe, our universe, positively expands out with a gaining entropy in one direction, and then the other universe increases in entropy out in the other dimension. If these are causally connected, which is not what the model says, but pretend you have a lay skeptic that says this, like Darren Lute, this is just ridiculous because right away that's a violation. If this second universe with a different time arrow is part of our past, then that proves that it's a violation of the second law of thermodynamics. You're positing that there is a high, initial high level of entropy, and that decreased until time zero, and then it started again increasing. That's a violation of the scientific law established with absolute certainty, the second law of thermodynamics, that entropy will only and can only ever increase. It cannot, physically impossible for it to ever decrease. So yeah, if a skeptic tries to approach you that way because he just has no idea what he's talking about, just call him an utter fool. No, I'm just joking. Just point out that's actually impossible. It violates the second law of thermodynamics. Nope. The world's experts, including Dr. Sean Carroll, the atheist, scientist who advocates these models, or the other scientist who advocates these models, they say, nope, two separate universes, and time zero is defined by the increase in entropy, and they're totally causally unrelated, and that's why we have the low entropy with entropy increasing in opposite directions for each of these separate, causally separate universes. And it's because they're trying to avoid a violation of the second law of thermodynamics, which is positively insane if you're going to deny that. So I just wanted to cover that in case, because you never know what you might encounter, right? You talk to all kinds of people, and some people aren't that knowledgeable in that, so they might say something like that. So that's how you'd respond to this. So yeah, the time deconstruction or time reversal models aren't actually eternal cosmological models. They're technically speaking finite. They prove that the universe began to exist. Our observable universe began to exist at a finite point in the past. It's not eternal, therefore it's not logically necessary, and by definition it is contingent thing. So I don't need to even refute those models, and that's why I've kind of left it out of the three criteria there. It's not infinite. It's a finite cosmological model. So yeah, there's really only three models that are even able to be infinite by their own definitions and that sort of thing. So just wanted to clarify that. But yeah, in terms of the infinite eternal inflation models that we have left, the three ones, let's get back in the criterion, look at the less ad hoc criterion, or the criterion of simplicity. How do they perform on that criteria? Okay, so in terms of simplicity, with infinite contraction models, these are immensely ad hoc because they have a certain ad hoc component, namely that the initial conditions of the model have to be set to an extremely fine-tuned way at the very start of the collapse phase from past infinity, just in order to be consistent with the scientific findings of the CMB, cosmic microwave background radiation evidence we have, given our early Big Bang point, right, after the Big Crunch to the Big Bang point, and the early history of our universe's expansion phase. What's even more problematic here for these models is that these specially fine-tuned initial conditions would all have to be exactly right and all cooperate with each other in order to result in the evidence that we see, despite them all being causally disconnected from each other. They would have been set in an a-causal way in the infinite past at the start of this infinite contraction phase. So the question of how mere mindless matter and energy in widely separated beyond the speed of light's ability to reach, and remember that horizon problem with the standard Big Bang, for example, at the start of the universe, and somehow have the quote-unquote know-how as to how to all work together just to conspire to give us the precisely correct, spatially homogeneous outcome to lead to our Big Bang moment and then our subsequent expansion. That chance alone, that's ludicrous. It's impossible that would happen. That's very ad hoc. The next model with ad hoc is the Frampton phantom bounce, or the Big Rip models, infinite cyclic or cyclical models. These are all of them are extremely ad hoc in that in order to avoid the implications of the BBG theorem, they have to suppose that the average contraction or deflation exactly equals the average expansion of the larger universe as a whole. And it must do that for every single patch universe. Given that these patches are entirely causally disconnected under this model, and the fact that the model must relate the expansion rate with dark matter to the deflation or contraction rate, without any dark matter, that suggests some level of intelligent design or fine-tuning. There's no plausible unintelligent natural mechanism capable of tuning the deflation scale factor, without dark matter, at least, to be able to precisely match the post-Big Bang expansion and that sort of thing. So extremely ad hoc. And this isn't even including some of the ad hoc elements we mentioned in the plausibility and the explanatory power section. So, yeah, utter failure on this front. 1% for both of these types of models. There's no ad hoc components to mention with the asymptotically static models that I was able to find in my research, but there's probably are some, but just put NA or assumed 100%. So yeah, these all utterly fail. If we use the less ad hoc criterion just as a tiebreaker and don't necessarily include it in the calculation, then the infinite contraction models turn out to be the best at assumed 100% for plausibility, assumed one, and then 100% for explanatory scope, times a generous 20% for explanatory power. That would be 20% there. I gave 10% to the asymptotically static models, probability of fulfilling the best explanation inference criteria. And then for the infinite cyclical models, like the phantom bounce model, remember, this one kind of failed on plausibility, which really hurt it. I gave it 20% on the plausibility criterion. I gave it 100% for the explanatory scope, and then only 5% for the explanatory power. So yeah, that would be essentially 1% if we just treat the less ad hoc criterion as a tiebreaker to help out these atheists and skeptics' eternal models. If we include ad hoc, then it's 0.01% because that one only got a 1% probability based on being less ad hoc or simple. But yeah, to do the worst case scenario against our argument to help out the atheists and skeptics, dropping the less ad hoc criterion from multiplying, just looking at the first three, infinite contraction, only a mere 20% probability that it fulfills the three criteria of plausibility, explanatory scope, and explanatory power. A mere 10% probability with asymptotically static models for fulfilling these three criteria. And in fact, that goes for all four of the criteria because there weren't any ad hoc components, so I'm not ignoring the ad hoc criterion there. And then finally, with the infinite cyclic, I ignored the ad hoc criterion and I got 1% total that it fulfills the plausibility, explanatory scope, and explanatory power criteria. So, 20% is the best model that we have. The infinite contraction models are the best of all the specified eternal models that we've looked at. Of course, 30% was the unspecified eternal cosmological model, compared to 70% for the unspecified finite cosmological model. So far, we're kicking atheist butt in these arguments. They're failing big time. None of their attempts are really doing the trick here. So, let's see how well they do with the next round, because we're not finished. There's a next round of eternal cosmological models that represents sort of a fifth exception to the BVG singularity theorem, and it's one of the 5 original exceptions, or to the Hawking-Penrose singularity theorem of 1970, and those rely on quantum gravity models. These are things like Roger Penrose believes, or Dr. Stephen Hawking went for a model in this category, and that sort of thing. So, yeah, that's what we're going to look at. Specifically, I'm going to limit these types of quantum gravity models to the models that are viable today in the 21st century, post the 2003 BVG singularity theorem. These are the models that we're going to look at. Before I do that, just wanted to make a quick correction note about what I just said with Sir Roger Penrose. So, his model, his conformal cyclical cosmological model, or CCC model, that's supposedly past eternal, basically that just kind of posits, okay, in quote-unquote sequential order, there's one universe expands to the point of heat death, and then a new universe takes over, and that sort of thing. So everything's gone except for photons, and then a new universe comes up, and supposedly this could go on eternally in the past. There's an eternal number of conformally cyclical universes and that sort of thing. Dr. William Lane Craig, one of his attacks about this is, oh, but if you have an A theory of time and you view time under this model, time actually doesn't isn't continuous from each universe to sequential universe, and therefore there is no sequence. And we have to say that the universe that we're in did in fact exist in the finite past and had a beginning in the finite past, even if we assume Roger Penrose's model is correct under, and it fits as an internal inflationary cyclical model. So that's the category that it fits into, not necessarily just the quantum gravity type model. Sometimes these models straddle both categories. But yeah, this model, Roger Penrose's models are very improbable to be true, as most cosmologists, physicists, and scientists don't believe that his model is in fact correct. And there's various reasons for that. So number one, there's that all cyclical models have that problem of the second law of thermodynamics, where it just forgets. Most scientists disagree with Roger Penrose that the effects that the thermodynamic properties would just be erased or quote unquote forgotten about as Roger Penrose's theory postulates. That's just improbable to be true. And secondly, it also has problems in thinking that only photons would be the only things existing. Other scientists believe that there's other issues, such as electrons would still survive, or other particles would survive, or something like that, and it wouldn't just be photons. Therefore, Roger Penrose's theory is improbable as an internal inflationary cyclical type model. So just wanted to clarify that quickly. But yeah, so let's get back into the quantum gravity models proper. So these are based on denying the Hawking-Penrose singularity theorem, denying the general relativity. It supposes, okay, but maybe the falsity of general relativity might work. And with the BVG theorem, that doesn't assume, like the Hawking-Penrose singularity theorem, that general relativity has to be true or governing the universe. It just assumes that on average the universe is expanding. There are models within the quantum gravity regime that are said to try to overcome this. So yeah, obviously with the universe, we know that it would shrink to a size at a certain point, 10 to the power of minus 43 seconds or whatever it is. It would be at the quantum scale. Therefore, GR would no longer apply to it. And quantum gravity, some theory, mystery theory based on quantum gravity type theories that can avoid a beginning of the universe and say that the universe existed eternally. So let's take a quick look at, there are basically three types of eternal models, allegedly eternal model here, that fall under the quantum gravity category or regime of eternal models. So there are string theories models, and there's at least a couple of those. So these are models, we kind of addressed this before with the string landscape theory, which has devolved because of problems with that. That's devolved into the string swampland hypothesis type models, and those are all, because of the BVG singularity theorem, those are all refuted and stuff like that, and really we're reduced down to just a couple models that might possibly work here. There's also the second category, which I personally think is the best. I actually struggled with this when I was studying this. So these are the loop quantum gravity cosmological models. And I think if you're an atheist or a skeptic, desperate to avoid the beginning of the universe, this is where it's at. This is really the best option that you have. It's relatively new in cosmology, but it's gaining a lot of traction. And personally, as we'll see when I get to my assessment, I think this is the best that the atheists have. And in fact, I almost thought a certain type of loop quantum gravity model defeated the Kalam cosmological argument, that we can this abductive argument would have been defeated. But ultimately, I'll get to that when we get to the assessment of those. But yeah, it's based on loop quantum gravity, and I'll explain that in a second. And then finally, we have a semi-classical type model. So it's outside, obviously the singularity theorems, the BVG and Hawking-Penrose singularity theorems, they apply to classical spacetime, and quantum gravity avoids classical spacetime because we're no longer where GR holds. We're so small, we're at a quantum level now, and that's no longer said to be classical spacetime. So loop quantum gravity and string theory, these are non-classical spacetimes. supposed. But then there's models in this category called semi-classical, so it's kind of in between and that sort of thing. So people like Stephen Hawking fit into this category with his no boundary proposal. And okay, so yeah, with that said, let me explain these some of the models that we're going to be assessing in these three categories of allegedly eternal cosmological model. Okay, so starting with explaining string theories. So basically, string theory-based models are based on string theory in general, obviously. And string theory, what it does, it proposes sort of a radical answer as to what constitutes the most fundamental building blocks of our universe. So most physicists, scientists, and world's experts in the entire world will always say that particles, fundamental particles, are the fundamental building blocks. Quarks, subatomic particles of certain types, like quarks, gluons, that kind of thing. And they'll say, well, instead of these positing some kind of, particular particles or zero-dimensional objects as the fundamental building blocks of the universe, they'll say, no, it's actually some kind of elementary entity called a string. And these are one-dimensional, so they have a minimum size. So in effect, it denies that the universe could shrink all the way back to a singularity, that point of infinite density, infinite heat and all of that stuff, because there's a minimum size. The universe can only get to that as small as a one-dimensional string and that sort of thing. So this is how it works. Obviously the strings constitute various dimensions. So there are the three strings. That's the three dimensions of space. And then they posit even more strings and that sort of thing. And this is called brane cosmology. And these exist within the a multi-dimensional, multi-stringed higher dimensional space type realm, and this is sort of called the bulk, so just so you know what the terminology is. Now, just so you know, irrespective of the various benefits and problems that string theory is able to offer, suffice it to say it's totally unproven that to be true. In fact, the physical evidence shows that it's probably not true. There are various problems with it. And it's very ad hoc, of course, positing multiple dimensions beyond just the three dimensions we know in terms of width, height, and depth. But yeah, like I said, its main strength is it posits this minimum size that the universe can get at the size of a one-dimensional string. And this will allow us to bypass the Hawking-Penrose singularity theorems and suggest maybe there is a before at this stage where the universe is past eternal. So the two main categories today are what's called PBBI, or pre-Big Bang inflation models, and then the second are ekpyrotic cyclical models. So these are the two categories of string theory models that people go for today. But just so you know, a major issue with the string theories is that they are totally irreconcilable with stable dark energy. And that's, like I said, most cosmologists believe in stable dark energy and that sort of thing. So this is right away something that makes string theory-based models very implausible and that sort of thing. But yeah, so let's look at each of these models. So, okay, what is the pre-Big Bang inflation, or it's otherwise called the string gas cosmology? So essentially these models are akin to if you remember when we looked at the eternal inflationary models, you remember the asymptotically static inflationary model that we examined? Well, the pre-Big Bang inflationary model is kind of like that. It sort of says that before the Big Bang, in the pre-Bang, Big Bang universe phase of our universe, that exactly mirrors the post-Big Bang universe with in terms of our post-stage, our expansion and that sort of thing, where the universe is expanding eternally into the future, presumably. Well, it's the same on the opposite side, on the mirror edge, in terms of the pre-Big Bang stage of the universe as well, in terms of being eternal in the past. And through gravitational contraction, they think that, okay, black holes would have then been formed, and once these black holes reach a certain critical value, the universe goes through a single big bounce into the Big Bang phase through quantum effects and that sort of thing. So yeah, the best of these pre-Big Bang inflationary models is that proposed by Dr. Gabriel Veneziano and Maurizio Gasparini, and they basically postulate that there were 4 phases in the development of our universe. And so these phases include, number 1, there is the eternic static, quote unquote, Milne phase of the universe, or what's otherwise known as the string perturbative vacuum, or SPV state. This is a state where it's totally empty of energy. It has an energy density of 0, and it's neither expanding nor contracting. It's static in that way. Remember, the BVG singularity theorem says that it only applies if the universe on average is expanding. Well, this is going to say, well, on average, if the universe is neither contracting nor expanding, it's static. Okay, so with this phase, then all of a sudden we enter a quasi-Milne phase, which is constituted by a quote-unquote perturbed SPV state, or string perturbative vacuum state. Then number 3, we enter the pre-Big Bang inflationary phase, where this model gets its name from, where the matter collapses into black holes and space expands regionally rather than globally, as we see it today, within what they call the string frame. So that's comparable to the Einstein frame. Remember what we studied some of the eternal inflationary models, we studied the Einstein steady state phase or something like that. This string frame is this model's equivalent or something. And then finally the 4th phase, the post-Big Bang FRW, which refers to the researchers finding the CMB radiation phase of the universe. So that's what we see today. There was the hot Big Bang, and then we have the evidence of the universe expanding forever into the future and that sort of thing. So yeah, you can see some helpful images of this model in action. Okay, so that's that model. The next model is the ekpyrotic cyclic model. This is a model advanced by Paul Steinhardt and Neil Turek, and they basically posit an open universe model. So the universe is not a closed system that would be privy to the second law of thermodynamics. Yeah, it basically says, well, look, periodically the branes, these bundles of strings together, collide in this higher dimension of the bulk, and that triggers a Big Bang event, and this happens repeatedly over the course of eternity and stuff like that. We just happen to be our universe that we see today that's expanding just happens to be the result of one of these collisions. In this way, it's a cyclical model, and they say, well, this cycle could have repeated throughout the past over the course of eternity and that sort of thing. Now, I'm just going to throw out here, without even getting into assessment, this ekpyrotic universe model, I'm just going to assess it out of the gate. It's false, and you're a fool if you believe that this is true. Because number 1, even the scientists themselves who propose these models, even they admit that they're not actually eternal in the nature, but they actually do posit a true beginning to our universe in the finite past. And they hide behind terms. You'll see terms in their papers that I link to called semi-infinite. What the heck does that mean? That's a trickery word. It means finite. If it's not actually infinite, then it's actually finite. Using trickery words like semi-infinite to describe your model is a trick on the part of scientists. Don't fall for that trick. And secondly, it's mathematically proven 100% to be false, because the BVG singularity theorem applies to this theory and falsifies it. It cannot survive the mathematical proof of the 2003 BVG singularity theorem. So this model has to be abandoned today. You cannot use it to posit an eternal thing. So therefore, if you want to go for string theory, there's only really one model, the pre-Big Bang inflationary model, that can even possibly be eternal in the past and account for the evidence that we have in terms of our aspect 1 features. Let's move on to the next category. And as I said, this is the best one. This is the one I kind of struggled with the most. It's the loop quantum gravity cosmological models. LQG models are much more superior to string theory-based models. They're a lot less ad hoc and a lot less ambitious. They have a very limited scope relative to the string theories, which try to upturn all of modern physics and stuff like that, and deny particle physics, which pretty much virtually every person with a PhD on the planet in science would disagrees with. Most of them do. That's an exaggeration. But so with loop quantum gravity models, once again, kind of like string scenarios or string theories, they say, well, with loop quantum gravity, there's a minimum size of the early universe. It couldn't have gone back to an actual infinite density, actual infinite thing, or a size of 0 or something like that at a singularity point. No, there's this space can be divided into discrete constituent parts, and these are called quote unquote quanta in loop quantum gravity models. So this represents kind of like how the strings are a minimum size of the universe. These quanta represent a minimum size that the universe could shrink down to. Past, and therefore, okay, well, maybe if it only shrinks down so far, it survives on the other side for past eternity or something like that. And once again, there are two main types of categories that qualify as loop quantum gravity models. So the first are asymptotically static models. Once again, remember that BVG theorem. It applies if on average the universe is in a state of cosmic expansion, global expansion. Asymptotically static models, which we evaluated in the eternal inflationary model, it says, well, no, on average the universe is neither expanding nor contracting. It's just static on average. And believe it or not, the asymptotically static model that we evaluated back in the eternal inflationary model is this model. This is one of the models that qualifies as both an eternal inflationary model and a quantum gravity model. So we already covered this and proved that this model is improbable. We don't have to go over that again. You can just go back in the video and listen to where I covered that under the eternal inflationary type models. But here's the one that's the hardest. There are also loop quantum gravity cyclical models, such as that advanced by Martin Bojewald. And those are the models that I find the best in terms of what the atheists have to offer. So yeah, cyclical models are based on loop quantum gravity. They have several advantages over string theory models that are string theory cyclical models, for example. So, for example, it doesn't need to posit additional unproven or ad hoc dimensions of space outside of the three that we know. It doesn't have to posit that there's quote-unquote free energy injected into the situation. It doesn't have to upturn all of modern physics and stuff like that. Further, recent scientific discoveries based on the power spectrum of the CMB radiation, the cosmic microwave background radiation that we covered in aspect 1, there is a tendency to favor loop quantum gravity models. So this is some evidence that seems to support the explanatory power of these types of models over and against eternal inflationary models. Yeah, there's some data out there that says, well, actually loop quantum gravity might be better than eternal inflationary models, which is what most atheists and skeptics are accustomed to bringing up in a debate on the cosmological argument. So that's interesting, and take a look on your YouTube video for some pictures of these types of cyclical models. But yeah, I won't get into the assessment yet. We're just explaining the model. But yeah, it's these ones where I kind of went, yeah, there's something here. This one seems like it's early days yet, but it could potentially serve as a defeater for an argument, for our abductive argument here, trying to prove that the universe began to exist in the finite past based on the scientific evidence from cosmology alone. Obviously, the two deductive philosophical arguments and my modal argument disprove this and show this is wrong, and that the two philosophical arguments prove that this can't be true. These models are false on that base. But yeah, again, this abductive argument, I'm trying to keep it independent of my prior philosophical arguments against infinities and an eternal past and that sort of thing. So great. So that's that. Okay, so we'll get into the assessment momentarily. But finally, we have the semi-classical models, and there are two main types here. So the first one I mentioned is the Hartle-Hawking no-boundary proposal by Dr. Stephen Hawking and James Hartle. And this model basically says it's kind of like a badminton birdie. So the universe, just like the Big Bang, it's like a cone. It's getting smaller, smaller, and smaller. But then by inserting imaginary numbers into Einstein's general relativity equation, this is why it's semi-classical, because it's using general relativity, the equations there. But inserting imaginary numbers in there allows time to convert into a dimension of space and function like a dimension of space rather than time. So, it's kind of like asking, well, what's south of the South Pole? There is no south, right? And what's before the Big Bang? There is no before. It just kind of time converts into a spatial dimension. And this is what Hawking calls imaginary time and that sort of thing. And as we'll see, that this is just complete rubbish. Imaginary time and using imaginary numbers in this way to come up with this notion of imaginary time is implausible. And again, we have those arguments for the A theory of time. So it's saying that time is a metaphysically independent notion, so that just disproves this model altogether and totally implausible. But here's the real kicker. If you're an atheist or a skeptic, let's pretend Stephen Hawking is right. I'll give you this model. It's not infinite in the past. It's not eternal. It actually says that the universe began to exist at a finite point in the past, time. It didn't go back to a singularity point, but who cares? No one believes that, right? Christians, I just proved that actual infinites are impossible. So I don't believe the universe began at a singularity point, but it still began at a minimum size or something at a finite point in the past. And that's all this model is saying, is that at some point space and time came into, from a timeless existence, or a tenseless existence, came into the temporal existence that we have today, from a timeless, rounded off and became time and that sort of thing, as the badminton birdie. That's all this thing says. So this actually proves, if this model's true, it proves the universe scientifically began to exist, and therefore our premise number 1 is upheld by Dr. Stephen Hawking and James Hartle. But there's another model here, and this is called the quantum tunneling from nothing model. And this is by Dr. Alexander Vilenkin. Remember that world's famous expert that came up with provides the V of the BVG singularity theorem, Bohr, Guth, and Vilenkin. So he basically says that he has his model where he thinks that the universe came into existence from nothing, quote unquote nothing, which is not really nothing. That's a lie on the part of scientists, a deceitful trick, because it's actually a quantum vacuum state with positive and negative energies that equal each other, have a net zero effect, but still there's something there. And from that state, it quantum tunnels and into the Big Bang universe that we have today, and into the Big Bang universe state. Once again, though, for atheists and skeptics, watch out, because even if this model is true, it doesn't say the universe is eternal. Remember, Vilenkin's the guy who's quoted as saying we have absolute proof, absolute, you're a fool if you deny it, that the universe began to exist, given his mathematical proofs. And that's not just the 2003 one. He's done post-work in 2012 proving that this is the case. So if we want to just take Vilenkin's model, the universe began to exist at some point in the finite past, you believe premise 1 is true, because the universe is not eternal, therefore it's not logically necessary, so it has to be contingent. Bada boom, bada bing. Thank you, skeptics, for conceding defeat to the Christian on this front. Okay, so now there is one thing, though. Why do these semi-classical models even get brought up in the debates about the cosmological argument or that sort of thing, then, if they're just totally useless and they admit that the universe began to exist in the finite past? Well, technically, it's more about denying a causal principle. Denying the notion that from out of nothing, nothing comes. And these models can try to at least claim to deny that premise. And that would be relevant more to in William Lane Craig's cosmological argument, everything that begins to exist has a cause. These models say, no, stuff can come out of nothing. Or in our case, with our argument from contingency, our Leibnizian cosmological argument, this might be used to deny premise 2, where it's the principle of sufficient reason, saying that everything that exists has a sufficient explanation of its existence, either in the necessity of its own nature or in an external cause. These models might be used to challenge that. We'll get into more assessment of that when we get into premise 2 of the argument. But just for right now, I just want to very quickly address this, because number one, it's a lie. It's not about nothing. It is coming from something. If you take the models at face value, everyone admits this. So don't be tricked by language. When they say nothing, they're lying. They mean something, and therefore that something provides sufficient conditions, and therefore a sufficient explanation or cause of the universe quantum tunneling into a new state. The classical de Sitter solution from the previous quantum solution in Vilenkin's model, quantum tunneling from nothing, and same deal with Stephen Hawking's model, the no boundary proposal. It's the exact same thing. So yeah, just understand there are three possible interpretations of these models. And number one is that the universe is literally created from nothing, and or nothing plus the laws of quantum mechanics, or some, a quantum field, or the laws of gravity, quantum gravity, something like that. Two, it is neither created nor destroyed, but just exists timelessly, in a timelessly subsistent way in this phase of its existence, Hawking and Hartle. Or it's ultimately a mystery. It has an explanation, but it remains unexplained at the moment. So the first interpretation is just logically and physically impossible. The laws of nature are not things or substances or property things in their own right that exist. They're simply mathematical descriptions of the way physical things are causally disposed to behave in given situations. So when it comes to the laws of nature, I did a blog on this. There's various interpretations as to what are the laws of nature. I take what's called a causal dispositions theory of the laws of nature. All they are is descriptions of the normal causal dispositions of physical objects or physical things. That's what they are. If there's no physical things, there's no laws of nature. I think that interpretation one is ridiculous and not true. Number one, it's a lie that it's saying that nothing exists. Number two, it's a lie to think, and logically fallacious to think, that the laws of nature can exist without physical things in it, with causal dispositions or capacities in it. The second interpretation is very problematic because, once again, as I said, Hawking himself admits that his notion of imaginary time, it's just instrumental, but it has no basis in real ontology. You're a fool if you believe that this is real in any way. His substitution of imaginary numbers into the equations, a flight of fancy that has no bearing on reality. Even Hawking himself has been shown to at least admit or concede that, this is a real problem. There's real issues with supposing that this notion of imaginary time could in any way be real or ontologically real in terms of a past phase of the universe. But it also leaves open that question of why, even if it's true, why would a timelessly subsistent state that is sufficient to bring about a temporal state, why would that only come into existence why would that temporal state only come into existence billions of years ago instead of an eternity past? Logically impossible unless you have God, a free will agent. That's the only escape clause. And again, we'll get to that when we get to premise 3 and stuff like that. But just wanted to give that. So really the final interpretation is the only way to make sense. It doesn't deny that the universe began to exist and was therefore caused and explained by any number of quantum mechanisms, whether that's a metastable ESS state or an SPV vacuum state, in light of the Heisenberg uncertainty principle, something like that, which, by the way, would rule out any notion of a zero energy condition, which is what scientists try to base their trick of saying that it came out of nothing based on this zero energy condition and stuff like that. So if you're going to take these models and pretend that these models are true, let's just grant these semi-classical models, the best explanation or interpretation of them is that, the physics proves the universe began to exist at a finite point in the past. It did not literally come from nothing, and indeed, it has a sufficient explanation and cause, even if it has to be left unknown or unspecified, because modern physics has no way of identifying that. And that's where we get into philosophical arguments proving that, no, we do know what that explanation is. It's God, and we can prove it philosophically. But if you're just going strictly on the science and you want to grant this model, You just say, well, we know for a fact it has an explanation and a cause, but we just don't know what it is. All right, great. So that's the models in a nutshell. Let's get into some quick assessment on the ones that are still in the game for being possibly eternal. Okay, so in terms of our best explanation inference criteria, the first criterion is plausibility. And from what I could tell, so once again, the semi-classical models are implausible because of their notion of imaginary time through the use of imaginary numbers in the gravitational equations and GR equations and that sort of thing. But again, they're finite in the past, so who cares? We don't even have to assess those. In terms of the live options, the ekpyrotic cyclical string theory model is totally implausible and lacks explanatory scope in terms of the BVG singularity theorem, because it just is not able to account for it. That theorem proves this is false and falsifies that theory. So those three models are immediately out of our assessment. In terms of the loop quantum gravity cyclical model, remember the asymptotically static model we assessed as under these criteria as part of the eternal inflationary model, so refer to that. But in terms of the loop quantum gravity cyclical models, they seem perfectly plausible to me. I think that the cyclical ones can be said to have plausibility or to fulfill this criterion. However, the remaining string theory one, the pre-Big Bang inflation model, struggles with plausibility. Only 5% proven on this in my case. Number one, because even the scientists themselves admit these are just toy models. They have no real ontological basis. There's question about whether they have a basis in reality, and the scientists themselves in the papers kind of flip-flop. Sometimes they pretend it is real, other times they admit it's complete rubbish and it's only a toy model. But what's more, even more devastating on this plausibility, is that the model's notion of this SPV phase, even if we suppose that it were to be real, well, then it would inevitably lead to a state that's finite in the past. It cannot be eternal or infinite in the past. If we do suppose that this SPV phase were not a toy, but were actually real. And this is especially because the model uses quantum tunneling from this SPV state rather than from the other quantum states of quote unquote nothing that Hawking and Vilenkin's models envision on those semi-classical models. But instead it says, look, it quantum tunnels from an SPV state to another state, and that SPV state must be real in order for the model to work. But that can't be eternal because it would be unstable, not just metastable, but unstable, inherently so. And it couldn't be static over the course of eternity. The universe wouldn't just be 13 billion years old, it'd be eternal. Because of this natural inherent instability of this SPV state, it would be impossible for it to be eternal. The only way really to avoid this problem and reestablish eternity is to think that the SPV region is unreal or instrumental, and that, once again, okay, great, then you're saying it's not real, it's just a toy model, and therefore we don't have an eternal universe in the past. And sorry, just to clarify what I'm saying here, because I just realized it's a little confusing, right? If there's this instability, the universe can't be eternal because the universe would be eternal. What the heck does that mean? So what I'm saying is that in this pre-Big Bang inflationary string theory eternal cosmological model, remember there are those four phases. So what I'm trying to say here is because the SPV, stage one, would be unstable, so therefore it's impossible for the SPV to be eternal like these models propose, and that from there, if that was true, then we would immediately see stage four of the universe as we see it today, expanding and stuff like that. Our universe as we see it today, that phase should have come into existence not 13 billion years ago, but eternally, at some point eternally in the past. The potential infinite past or something like that. It couldn't have just come into existence 13 billion years ago if that's the case, because we couldn't have had an eternal SPV state. And then the stage four of the universe, the FRW phase of the universe that we see today, where it's expanding and stuff like that, only came into existence 13 billion years ago. That would be impossible. The instability of the SPV stage would have ensured that it would have come into being way before 13 billion years, and or potentially an infinite amount of time ago in the past and stuff. But obviously that's not the case. The universe that we see as we see it today, aka stage 4 as per this model, has only been around for 13.82 billion years, thus disproving that this model could be true. I hope that clarifies what I was saying there. So that's on plausibility. As I said, with explanatory scope, the ekpyrotic cyclical model doesn't account for the BVG singularity theorem. That falsifies it, and it has a 0% probability. But yeah, in terms of the remaining models, the PBBI, pre-Big Bang inflationary string theory model, and the cyclical loop quantum gravity models, I think that it fulfills the explanatory scope criterion here. Now we come to the all-important explanatory power criterion. How well do these explanations or hypotheses explain the data qualitatively? And here's where they all fail. Okay, so first of all, with the ekpyrotic cyclical model, again, it can't explain the BVG singularity theorem, so obviously it lacks explanatory power. And it also struggles, just like the emergent inflationary models we discussed in the eternal inflation models above. There's 0% probability because it would have to be semi-infinite. It couldn't be totally actually infinite, as even Dr. Paul Steinhardt himself, the proponent of this model, admits. In terms of the pre-Big Bang inflationary string theory type model, this lacks explanatory power because even the scientists advocating for this model admit that SPV region, it's not merely metastable, so that means slightly unstable. It's actually unstable, radically unstable, making it impossible for it to be eternal. And we kind of covered that with the plausibility aspect. So yeah, even if this model were true, were to be real, it could not, by definition, be eternal in the past, because there would be a near infinite number of quantum perturbations or disturbances of any size, even of the smallest size, would inevitably disturb this initial SPV state. Remember, we mentioned those 4 phases, and thus the lifetime would have to be finite, even if this model were true. So because of that, it's only 5% proven fulfilled in terms of this model envisioned as an eternal model to be fulfilling explanatory power, and that's me being generous to the atheists and skeptics. What about the cyclical loop quantum gravity model? So I said here these are the best models, and so far it's fulfilled plausibility, it has fulfilled explanatory scope, it explains all of our facts from aspect 1, or at least purports to. Okay, but how well does it do that? What is its explanatory power? And once again, it does have explanatory power. There have been empirical findings that do lend credence to the truth of these models, even over and above eternal inflationary models, which have been the most popular among atheists and skeptics trying to dispute cosmological arguments. Further, what's more, this model solves a problem. Remember, the pre-Big Bang inflationary models and internal inflationary models usually suffer from what's called BKL chaos, this turbulence, this instability or metastability issues at the moment of the big bounce. But loop quantum gravity perfectly solves this because it's been shown mathematically that if these models were true, again, there's a minimum size based on these discrete loop quanta, as they're called, so it can't decrease beyond that in terms of the universe's size globally. And because of this, in loop quantum gravity models, it dramatically calms this BKL chaos issue. And certain idealized versions, very ad hoc, but there are idealized versions of these types of models that do provide feasible solutions to this issue of instability and or metastability in this phase of the universe's history. So far, these loop quantum gravity models are doing pretty good. And, there are other issues as well. And I think that they have good solutions to it that Again, because I have the burden of proof as the claimant here, the theist is claiming they can prove God exists because, number one, they can prove that the universe is contingent, premise one, on the basis of the fact that we can prove scientifically in this argument that the universe began to exist. So the burden of proof's on me, not on the atheist scientists here, and I think that they provide equally possible or probable answers. They haven't proven that their answers are true, that their models are in fact true. Obviously, none of them can do that. It's pure speculation and ad hocness and stuff like that. But on all these issues, I don't think that the theists can prove that they're improbable. So there's a 50-50 chance there in terms of them being true versus the finite model. However, there is one major snag that I found shows that these models are less probable than the unspecified finite model, and this is the issue of thermodynamics and entropy buildup. This is for all cyclical models. This is always the issue for them, is this buildup of an inevitable buildup of entropy that proves, in light of the second law of thermodynamics, the universe could not be eternal in the past. And loop quantum gravity cyclical models are no exception. They suffer from this problem too. Now, obviously, the scientists are aware of this, and there's basically three solutions they try to desperately provide to avoid the truth here. So the first of these is they just say, well, this problem is merely epistemic in nature. It's rooted in our lack of knowledge about entropy and how it works. This is complete rubbish. Like I said, the second law of thermodynamics is so firmly established. It's the field of science that we know with absolute certainty, or near absolute certainty. So much so that world-famous atheists and skeptics, who are scientists, have even said, "Look, this is the linchpin. If your theory contradicts the second law of thermodynamics, you're wrong. If if it violates general relativity or some established law of nature, then perhaps the laws of nature need revising. If it violates the laws of thermodynamics, you're wrong. Get a new theory." So this is how strong this evidence is. Epistemically, there is no doubt it's right. And even Sir Roger Penrose has proven this mathematically, that this option isn't true for the atheists and skeptics who want to go for this model, because we positively and absolutely know that the amount of entropy from the Big Bang should differ from our observations by a factor of 10 to the power of 22 if these types of models were true. And further, that the size of the inflationary patch under these types of models should be much, much smaller than it is, given the thermodynamic criteria of the universe. So yeah, this just is an utter failure on the part of atheists and skeptics. And okay, but they're not done. They have a different option here. So they give a second little escape clause on this entropy issue. And that's that they try to say, okay, well, maybe it can be argued that our understanding of entropy is misleading because we're only restricting our focus to the entropy of matter in the universe, matter entropy, instead of including gravitational entropy. That's the solution. So number one, the solution is ad hoc and would be improbable, very ad hoc and improbable on that basis. But even more damning and devastating in terms of explanatory power is that, okay, let's pretend that's true. This still doesn't resolve the entropy buildup issue that these models suffer from, because entropy would still build up and accrue, even if Penrose may have overestimated his own calculations and mathematical proofs by excluding gravitational entropy considerations. It's still going to be the case, inevitably, that entropy is still conserved, at least to some degree, from cycle to cycle over the course of eternity, and would therefore build up, making it scientifically impossible and physically impossible for the universe to be eternal in terms of having an eternal past of various loop quantum cycles going on. Okay, finally, the atheists and skeptics have one last ditch effort, and this is the best option that the atheists and skeptical scientists who go for loop quantum gravity will say, is they'll boldly argue for a violation of the second law of thermodynamics, and they'll just say, well, maybe somehow, some way, the overall entropy of the universe decreases or is even, quote unquote, erased Remember, Sir Roger Penrose has this notion too. At the moment of the big bounce in loop quantum gravity. But yeah, as I said, an outright denial of the second law of thermodynamics is insane, literally insane. And the vast majority of scientists are skeptical. Cosmologists, by and large, do not agree with this notion that the entropy decreases and or can be erased at the moment of a big bounce and stuff like that. And this is especially the fact because Dr. Aaron Wall, the world famous Christian cosmologist, has proven, and I provide a link to his article where he proves that the generalized form of the second law of thermodynamics applies at the level of quantum gravity as well. So you can't escape the second law of thermodynamics by appealing to quantum gravity or something like that. In the same way, you can escape general relativity or relativity theory by escaping to a non-classical space-time notion or to the quantum realm or something like that. So yeah, this third option is the best that they have. It's purely ad hoc on their part, so obviously it's very improbable on that basis. But even still, like I said, the physical evidence we have and our understanding of entropy says that this is very improbable, that the entropy would decrease or be erased at this moment, and that includes at the quantum level as well. So I assigned about a 50% proven fulfilled level for the explanatory criterion for the cyclical quantum loop quantum gravity models, eternal models here. So right away you can see this is the best, right? Because so far all of them have been way like about 10% or less or something like that. The best we've had was the unspecified eternal cosmological model at 30%. But here we have a specified loop quantum gravity model. In terms of explanatory power, I'm about 50% convinced. It seems to me that on the basis of the evidence and our scientific knowledge that maybe somehow the entropy could be erased or decreased. But yeah, it's very speculative. Like I said, the majority of cosmologists and scientists on the basis of the physical evidence would say that this doesn't and can't happen. So yeah, I assigned a generous 50% on these models in terms of explanatory power. All right, in terms of ad hocness, so obviously I covered all the ad hocness of loop quantum gravity above when I covered the explanatory power things. I didn't count that against the models just because I wanted to be generous to the atheists and skeptics, so I'm counting the less ad hoc or simplicity criterion as kind of a bonus criterion now. But yeah, just in terms of simplicity, just something I didn't mention. In terms of the pre-Big Bang inflation string theory models, those are ad hoc in relation to dark energy. They just deny that there's dark energy and stuff like that. And on that basis, I think that they're very ad hoc. All right, so great. So yeah, we see the cyclical loop quantum gravity models come in have an overall probability of 50%, 100% on plausibility times 100% on explanatory scope being fulfilled times 50% on explanatory power, and then not applicable on the simplicity. So that equals 50% proven that the cyclical loop quantum gravity models fulfill the best explanation inference criteria, and that is the best ones. In terms of the string theory PBI, that's less than 1%. It's about 0.25%. The ekpyrotic cyclical models are 0%. They just by definition can't account for the BVG singularity theorem. And then the asymptotically static models, loop quantum gravity. Well, remember, we assessed that in the eternal inflation thing above, and it got 10% proven that it fulfills the best explanation inference criteria. And then we have these semi-classical quantum gravity models. And once again, look, they are 0% or not applicable in the sense that they don't actually posit an eternal universe, but a universe that began in the finite past. So we don't have to worry about those. So yeah, like I said, 50%. This is the best atheistic option. And if we compare that to the 70% proven that the unspecified finite universe cosmological model is true, Well, 70% is greater than 50%. Therefore, we've done it. These are all the models. These are all the options. We've proven that on a balance of probabilities, the unspecified finite model, the cosmological model that is unspecified but does say that the universe began to exist at some point in the finite past, doesn't specify when that might be, 6,000 years ago, like young universe creationists, or 13.82 billion years ago, who cares, doesn't matter. I give 70% probability that the notion that the universe began to exist in the finite past is the best explanation here, beating out the best alternative, which is only at 50% proven in this respect. So, great, grand, and groovy. We've just proven the universe began to exist is the best explanation based on the scientific evidence from cosmology. Excellent. All right, so now what do we do in terms of wrapping up premise one and our overall conclusions here? So the first thing to do is, okay, well, given that we've completed our abductive argument, what is the overall probability that this abductive argument proves the universe began to exist? Well, so if you remember, there are a few components to this abductive argument. So the first component was the overall significance, right? So we're trying to establish that the unspecified finite cosmological model is the best explanation. It best fulfills the best explanation inference criteria, and we've shown that and that sort of thing. But the first question we asked at the beginning of this argument is the significance of that. Okay, so what? Let's pretend you do prove that the universe beginning to exist in the finite past is the best explanation. Well, that doesn't prove it's true necessarily, does it? And on this front, I gave a very atheistically generous and hyper skeptical or radically skeptical significance of 85% proven in terms of its significant level. If a given hypothesis best fulfills the best explanation inference criteria better than all the other alternatives, then I'm 85% certain that that proves that that hypothesis is in fact true. Now, in reality, I'm much higher than this because this has been established in science, logic, philosophy, law, history. Everyone admits that inferences to the best explanation are actually prove that the best explanation is probably true. So it would probably be 95% or something like that, perhaps even proven beyond reasonable doubt. So 95.01% or more, that the best explanation is in fact true. But again, I'm trying my best to help out the atheists and skeptics as much as I possibly can. So I went with a very low, radically low, 85% proven in terms of the significance of these criteria, proving that the best explanation is in fact true. Great. Okay, so that's the significance of it. But, okay, did we prove that, in fact, the universe beginning to exist in the finite past is, in fact, the best explanation? And on this front, we had two aspects or components to our argument. So the first aspect was where I proved all of those scientific facts and features. Remember, the cosmic microwave background radiation, the singularity theorems, the Friedmann-Lemaitre singularity theorem, the light element abundances, the hydrogen and helium being abundant in the early phases of the universe, as well as the cosmic expansion from the redshift data. And then finally, we have the thermodynamic properties of the universe in light of the second law of thermodynamics. So we had those two things. And remember, on the basis of those two scientific categories, on those scientific evidences, we said, yep, it's 99.95% proven that these evidences are true and that they seem to indicate the universe began to exist. Great. Then we looked at aspect number 2, which is what we just finished evaluating in part 3a and part 3b, and that's basically proving that my unspecified finite beginning model is the best at fulfilling the best explanation inference criteria compared to all the other eternal cosmological models, either unspecified or of the specified variety. And I established that was 70% proven versus 50% for loop quantum gravity cyclical models. So that's 70% proven here. So now we just multiply all three of these necessary components for my abductive argument. So we have 99.95% proven for aspect 1 times 70% proven for aspect number 2 times 85% in terms of the significance level of proving the best explanation is in fact true. And that gives us a total of 59.47% proven that it's true the universe did in fact begin to exist at some point in the finite past. So it's just slightly under 60%, and this seems true to life. It fits. This is about where it's a little bit lower than where I would have predicted I would have come out of. I would have predicted I was somewhere in and around 70% to 85% convinced, or about 80% convinced myself. But yeah, when I went through it as in the most rigorous way I possibly could, it turns out actually based on the evidence I'm personally have a little bit less warrant than I would have predicted. So I'm just under 60% at 59.47% proven on the basis of this argument that the universe began to exist. If it began to exist in the finite past, it's not eternal. If it's not eternal, it's not logically necessary. Therefore, I've proven the universe began to exist from this argument in isolation at 59.47%. Now, this isn't the only argument that proves the universe began to exist at some point in the finite past. Remember, we had two philosophically deductive arguments in addition to this abductive argument based on the scientific evidence from cosmology. So what's the cumulative total that we can prove the universe did in fact begin to exist, therefore it's not eternal, therefore it's not necessary, and it's therefore contingent. It is a contingent existing thing, which is what our first premise says. Well, let's do the math. Okay, so if you remember, the first deductive philosophical argument was for the finitude of the universe's past history. So saying that, as a matter of fact, our universe is not eternal, was based on the impossibility of there being an actual infinite. That was a very strong argument. That's our strongest argument in this respect. That came out to proven beyond reasonable doubt, 95.01% or more. I was actually 100% personally, but again, I gave that range and I wanted to give some measure of doubt in that, so I went for the benefit of atheists and skeptics, counting against my argument. We assigned the 95.01% as a lower limit for this argument, proving that the universe did begin to exist in the finite past. Then we had the second deductive philosophical argument. And that was based on pretend actual infinites are possible, but this one argues that a specific type of infinite is impossible. So it's the impossibility of forming an actual infinite through successive addition, one time after another. And if you remember in part 2, I believe, of my cosmological argument series, where we covered this argument, this was an argument that is time theory dependent. So this one depends on the A theory of time being true as opposed to the B theory or the A-B hybrid of possibilism being true and that sort of thing. If the A theory of time is not true, then this argument fails. And we discovered this one gave 77.9% degree of warrant that proves the universe began to exist based on this argument. And then finally we have the one we just finished in part 3a and part 3b, which is our abductive argument based on the scientific evidence from modern cosmology. And as I just said, that came out to 59.47% in terms of my degree of warrant. Okay, so now we plug those numbers into Bayes' theorem to get the cumulative total of all three arguments combined in terms of proving the overall probability that the universe began to exist. And as I said, this comes out to 98.99%. So proven very, very improbable that the universe could be eternal and therefore logically necessary. If it's not necessary, it's been proven beyond reasonable doubt to the degree of 98.99% that the universe did begin to exist as a matter of fact at some point in the finite past. It's not eternal, therefore it's not logically necessary. What else is there? That means the universe is contingent. And that's just based off this category of evidence. So we had, if you remember, in part one of my cosmological argument, I also provided other arguments that, independent of proving the universe factually began to exist, let's pretend the universe is in fact eternal. We can still prove that the universe is not logically necessary, but is contingent. And I did this on the basis of two modal arguments. So my first modal argument was basically, I argued, if you remember in part one, or go back to my part one video to refresh your memory on this one, but it basically just says, well, look, it's logically possible or conceivable that a different universe and or no universe at all existed. So there are possible worlds where a different universe exists, and or there's a possible world where no universe exists. And I appeal to even atheists admit this, because they can obviously use their modal evaluating faculties to conceive of a world where God exists alone and he doesn't create anything, and they can seemingly judge and say, well, that world is better than this world because this world has evil, or this world has the hiddenness of God, or this world has whatever. So even atheists confirm this argument, and that proves at a 95% degree I gave. Again, I was really at the 100% proven, but I cheated in favor of the atheists and against my argument, and assigned a lower limit of 95%. I gave skeptics reasonable doubt on this first modal argument. Now, I gave a second modal argument, and that was based on the possibility that our universe began to exist. So again, pretend it's a fact that our universe is in fact eternal. In this argument, I was saying, but we can still conceive of our universe. There are possible worlds where our universe began to exist and in the finite past. And this argument, I assigned 95% proven to this, but I realize now this is totally wrong. So I'm totally ignoring this second modal argument from our calculations, because if you think about it, I'm wrong here. Number one, we can't, because our universe only exists in one possible world, and that's the actual world. Every other world where we picture a universe like ours, that's actually a different universe, because our universe is a property thing. It's not a substance. It has no trans-world identity. So I was mistaken here. And because of that, I'm ignoring this argument. Basically, property things don't survive like substances do. They can't have trans-world identity. If you change the physical properties or parts and or the relations between that, it doesn't survive. It's a totally different thing. So in that case, yeah, what we're really saying here is, well, I can picture a universe that's like ours, that's not eternal but began to exist. So it has a different relations, and it has different properties and parts, right, that are surviving, possibly, different relations, basically. If we envision a universe that exists for 14 billion years, that's a different universe to our universe. So this argument just fails. So yeah, our specific universe as a property thing only exists in the actual world. There are no other possible worlds where our universe exists, and for that reason this argument fails. What we're really doing is providing more proof for our first modal argument by coming up with ways to conceive of a different universe, one that's very similar to ours and or even exactly the same up to 13.82 billion years ago, but then beyond that, it has different properties, parts, and or relations, physical relations, and is therefore a different universe. So I hope that makes sense. So yeah, we've got two essential categories of arguments that survive here. We've got one, a modal argument that says it's possible that different universes exist in possible worlds, and or that no universe could exist in a possible world. Therefore, it's the definition of being logically necessary that the proposition is true and or the thing exists, our universe exists in every single possible world. If there's even one possible world where it doesn't exist, our universe doesn't exist because it's replaced by a different universe and or no universe, just having God exist or an angel exist or something like that. God exists alone, for example. That proves that the universe is not logically necessary or metaphysically necessary. and therefore the universe is contingent. And then, like I said, the second category is the one we just finished in the last several parts. Part 1, 2, and 3A and 3B. We can prove as a matter of fact that the universe is not eternal but began to exist. If that is a fact, then that proves the universe cannot be logically necessary, because it's an essential condition of necessity for something to be eternal. If it's not eternal, it's not logically necessary, and it is therefore contingent. So yeah, let's see how we do there. So in terms of my overall argument, premise 1, we're finally at the end. What is the total overall probability that premise 1 is true? Remember, premise 1 of my cosmological argument here, my Leibnizian cosmological argument, or argument from contingency, simply says, look, the universe, and or the universe plus, if we're taking into effect the multiverse, the wider cosmos, is a contingent existing thing. And if you remember, there are two aspects to this that I mentioned in part 1, the part 1 video. So aspect number 1 of premise 1 was proving, well, the universe has to be an existing thing. And I described, well, number 1, the universe is a thing. Specifically, it's a property thing as opposed to a substance or a heap. And secondly, it exists. It is an existing thing. And that was 100% proven. Then with aspect 2, which we spent the bulk on, we proved that the universe is in fact contingent with those arguments I gave. So yeah, in terms of the totals then, for aspect 2, so we have 99.99% that, based on the three arguments that the universe in fact began to exist. We have 95% from the first modal argument that it's possible that there's a different universe and or no universe worlds at 95%. So combined, aspect 2 has been proven 99.95% proven true cumulatively if you plug those numbers into Bayes' theorem. And then, okay, great. So what's the exact total, that degree of warrant that we have for premise 1? Proving that the cosmic fact that needs to be explained, aka that the universe is a contingent existing thing. So we have aspect 1, that it's an existing thing, 100% proven, times aspect 2, that it is a contingent thing, that it is contingent, at 99.95% proven, or degree of warrant. 100% times 99.95% equals 99.95% final probability for premise number 1 being true, proven true, or having that degree of warrant, showing that it's a warranted true belief. Again, these are based on my own subjective probabilities. As I've always argued, there are reasonableness ranges. You may vary a little bit. So even if you might assign slightly different numbers, still the reasonableness range is very small, because the evidence that I presented in this respect is conclusive in terms of the contingency for the universe. So yeah, even if there is maybe some small flexibility, like I'm 99.95%, maybe you come out to 99% or something, or 98.7% or something like that, I think that it is proven beyond reasonable doubt. And there's a very small window here in terms of proving the contingency of the universe. If you're less than 95%, there's something wrong with you. You are unreasonable, given the strength of the evidence. You are unwarranted. I would definitely say that. So unlike other things, that reasonableness range, as I call it, is very small in this specific case, where we're talking about the proof that the universe is a contingent existing thing. So yeah, that does it for part 3B. Wow, finally, it's, after I think 12 hours, I've done approximately 4 3-hour shows over the past couple years, just trying to establish this cosmic fact that the universe exists contingently, or is a contingent existing thing. I am so pleased. Finally, probably within the next couple weeks or so, I will have part 4 of the cosmological argument, and that's where we finally move on to the second premise, right? So if you remember, atheists and skeptics have 5 objections to any cosmological argument, including our one, and it's anyone, Kalam, Thomistic, whatever. So Number one, we have to establish there's a cosmic feature. In our case, that is the fact that the universe exists contingently, so an atheist can deny that. We've proven that they're unwarranted or unreasonable if they do that based on the last 4 shows. Parts 1, Part 2, Part 3A, and Part 3B destroy that objection of the atheists beyond all reasonable doubt. The next objection is the Glendower problem, and that is the fact that, okay, great, you've established this cosmic fact, but so what? Does it need a cause? Does it need an explanation? And that's what my premise 2 is going to be saying, that yes, given we've proven this cosmic fact that the universe exists contingently, this requires a sufficient reason or a sufficient explanation for this fact. So that's going to be premise 2 of my argument. Obviously, premise 3, that's where we get into, well, what is that explanation? God, multiverse, infinite regress, whatever it is. So yeah, that's what to look out for. In terms of my cosmological argument solo series. Within the next 2-3 weeks at most, I will have part 4 up and ready for you, establishing the warrant for premise 2. That is basically the principle of sufficient reason. Everything that exists has a sufficient explanation or sufficient explanation of its existence, either in the necessity of its own nature or in an external cause. So that's a wrap. Have a great week, everybody. Take care.